Great. So Sadas Shankar is a great physician / physicist / neuromorphic engineer, I say, right? And we're very much we're delighted to have him in the workshop. And this will continue the thread of different foundations, and now really linking to also the foundations of computing. And so that's very important for much of what we do here in the workshop. So definitely was very applicable. So that's a good background. I won't always get this here at Harvard and based up there now at Stanford. In fact, at Stanford, there's something called Slack. Right. And so this Slack stands for the Stanford.
Without the Slack.
Yeah, yes.
It's not a Slack.
It's not a Slack that we have in constraint optimization. Although we'll get that too. That is the linear accelerator, right?
That's right.
Yes. And so that's a national, it's a UV.
Yeah, it's a now. Yeah.
But doing a lot more than high energy physics. That's so this will be foundational, Turing, von Neumann, and Wiener, and all that is very important. Whether you're in neurocontrol or whether you're in acoustic auditory optimization or quantum or right, so they're all very applicable foundations. In fact, Sadas is giving 2 talks, one now, which is the foundations of computing, and tomorrow you have another talk where we'll be diving into energy efficiency and really just, after all, we care very much about making systems that are not only doing great, but also inspired by the extreme efficiency and the resilience of neural systems. So, please.
Thank you, Gert, for your gracious comments, and thank you for the invitation. Something to join us. It has been actually a fantastic meeting, and I've been enjoying myself so much. I mean, I'm kind of kicking myself why I didn't know about this meeting before. It seems like so much fun. It doesn't feel like work, even though I'm working most of the time. So thank you all for coming. So I actually talked to Gert and something quite a bit about what the presentation should be, and I have used their inputs. So the talk will essentially try to, it will try to address 4 questions. What are the problems in computing from the perspectives of physics and thermodynamics? So it's a general talk. And can we recast computing to connect natural and human-made devices? And the third is how energy efficient are algorithms and software. You don't hear too many discussions of that, so just trying to get into it. And then if you're a physicist or a chemist, how to design a computer from physical first principles. How do you use physics to design a computer? I'm hoping to address these questions reasonably in this talk. So this is the agenda of the talk. There's a lag here. So I'll start with a few of the puzzles in computing that is over 60 years old or even older. Then I will kind of touch upon the problem of energy. The ones which are cut, I will not talk to this. So depending on the interest, I can get to that in the second talk. Then I will kind of show the logical framework, what the formalism is, illustrate then and apply it to simulation quantum chemistry on a digital computer, quantum chemistry emulation on a quantum computer. So I will show how this formalism can be applied. There's a part 2 to the talk. Again, I will not touch on this. We have extended this to neuronal synapses and also fluid flow and cellular metabolism to show how self-consistent this formalism is. And then algorithms and software, and we'll go back to the puzzles. So what are the puzzles in computing? I have tried to capture this in figures because figures mean a lot. I will let you recognize who the people are. Some of them you may recognize, but I will not have the time to go through all of the puzzles that we are trying to address. Okay? But the first one I'm going to try to address is Feynman's puzzle, which he posed in 1964 in Messenger lecture at Cauwenberghs. Infinite logic for a stinky, tiny bit of space-time. This messenger lecture was written as a book called The Character of Physical Law. But in that particular book, they have taken this quote out. So that's why I put the quote back in. Okay, so I'm going to actually let you hear it from the master himself. Hear it in his own words again.
It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, and no matter how tiny a region of time, according
Oh, it's muted. It's muted.
that why should it take an infinite amount of logic to figure out what one stinky tiny
See, it stops.
Oh, wow. That's interesting. That's not engaging. Give this one just a little bit on.
And repeatedly more. So I'm here to play this again.
it always
Okay. So you will get it to the lab, we'll have readings for more. Oh, interesting.
And it sounds like the audio is linked. You have to take the volume off.
Oh, I have to keep that.
It seems to automatically mute. It's okay.
Because I can hear you.
It's okay. I can share it.
So we should look at this. Stop sharing.
I think on Zoom you should maybe, can you just mute Zoom? So that you don't get the audio from.
So I stop sharing.
It's hearing.
Tell me what. So you can hear it here because it's not.
But quite honestly, we can keep both because we can barely hear the laptop.
You cannot hear.
No, it's like, so we do it to share the screen.
Okay, so let me share. Thanks. I'm going to share the desktop. I'm going to this. Okay.
it always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, and no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? That why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do? And so
you heard that, right? So he posted in 64. Sorry. So you heard that, you heard what we said. Now I guess I can put it on the so now I'm going to show what he meant by that by a specific example. This is the single coronavirus. Okay. When it affects humans, there are about 1 million infectious units per person. This is called a virion particle. And 1 milliliter of sputum contains about 10 to the power 7, about 10 million viral particles. This is when you know your cell has been infected. Okay? This is the pathway. I mean, I'm working on the metabolic aspects of this, but that's not part of this talk. This is the pathway the virus takes in order to infect this. All I want you to take away from this is the complexity of what a single virus is. Okay. Now, in 2020, the Gordon Bell Prize was awarded to simulate in the COVID-19 one virion particle. One, okay, not 10 million, one. It was done using supercomputers. And you can see the number of teraflops. These numbers don't mean much at this point. We'll get back to it later. The simulation was run for about 9 days. This is the highest, farthest end, the Gordon Bell Prize. And they had so much of this GPUs, CPUs, generated 200 terabytes of data to do this virion particle. This is the computer on which it was done. 340 tons, 185 miles, 250 petabytes of memory, all generated for use to simulate. 13 megawatts of power. Now you understand what Feynman meant. We simulated just one virion particle using this machine. The virus doesn't have access to the supercomputer, right? But it is doing its job. So how does it do it? Is it computing? Is it information processing? We don't know. So that's why it's a puzzle. The second puzzle was by Cyrus Levinthal in 1969. He made an estimate of the number of ways in which proteins can fold. And if you were to go through a combinatorial calculation, you can do it, and I will show you the numbers later. It can go up to 2 to the power 50 ways in which it can essentially go there. 10 to the power 50, sorry, which is a huge number of combinatorial. But all the proteins are folding. Humans have 37 trillion cells. All of them are generation proteins. 500 million reactions happen in every cell per second, over 37 trillion cells. There's no way we are understanding how nature is doing its information process. So now, let's say we have Moore's law. I worked at Intl for 20 years. So Moore's law was a big thing. It was almost like a religious thing for us. So I tried to recast this, that if we continue this Moore's law, can we solve these problems? Before that, I need to explain classical and quantum computer, because you have heard this before. There are many definitions of it. For practical purposes, a classical computer should have 3 aspects to call it a classical computer. There should be discrete states, there should be measurable states, and you should have control over them. Only then it's called a classical computer. Similarly, there's an equivalent for quantum computer. This is what is called a block sphere. I can explain it later, but it's not relevant. You have heard people claim a lot of things are quantum computing, but in order to call it a real quantum computer, you need to have 3 aspects again. Superposition, that's local, but superposition can be done in classical systems, as you saw in Rahul's talk. Entanglement and control. There's a physicist, David Davidson, who in 2000 put a whole set of attributes for scalable quantum computer. But to be minimally, to call something a quantum computer, you need superposition, entanglement, and control. Without that, you are actually using quantum inspired, not quantum computer. There's a difference. And I will not go into the details. So now let's look at Moore's law, right? So this is taken over 50 years. Number of transistors, Carl May postulated this. So taken till 2020, and you can follow that it's a logarithmic plot, semi-logarithmic. This is years, and you can see that it's doubling for 50 years. Okay. So I got the numbers, assume that we have 48 years because I actually have the numbers. So if you put Moore's law, it is equivalent to 24 doublings because it doubles every 2 years. So 48 years, you have 24 doublings. Very simple calculation. I don't know how many of you know, but our lungs have 24 doublings, all the way from the top to the bottom. Essentially, mammalian lungs have up to 24 doublings. So what we call 50 years of Moore's law, we are all carrying around. It doubles all the way till it gets into the blood. That's how the air is interdispersed with blood. So that is, nature does it through evolution very systematically. So now if you look at the length scales, all the length scales in physics that are on Earth, you have 27 orders of magnitude. So if you want to simulate the largest system using the smallest system, you need 27 doublings, a little bit out of the reach of Moore's law in 2020. If you look at biological time and length scales, you have 40 and 33 doublings. So it's much more beyond the Moore's law if you want to simulate the slowest process using the fastest process. So this is the ratio of the slowest process to the fastest process. Okay. If you look at the number of chemicals at mesoscopic level, atoms in devices and devices with interfaces, so for mesoscopic systems, their doubling possibilities are of the order of 100. Okay. And if you want to look at Levinthal's protein folding problem, it has 158 doublings. So even if you continue the Moore's law, there's no way you'll be able to simulate the protein folding from first principles. Do you see that why computing trajectory in the best case scenario will be hard pressed to simulate things in nature? So now I'm going to show you the problem of energy. So I showed you the problem of complexity. Now I'm going to show you the problem of energy. This is the same plot as I showed before, but normalized with respect to 1, so that I can show both the number of transistors and the frequency of the transistors. If you look at that, in Intl, around since early 2000s, the frequency was kept constant because power was a problem. So they kept the power constant and kept doubling the transistor. Without frequency, you can't get the speed that you got before. So we as users will see a slowing down in applications. Things will look not as fast in the next generation of computer as the previous generation. That's the way we see. Now I'm going to show you actually numbers of energy estimates. The reason it goes like TikTok is you will see the scales are too big to have it in the landscape. So this is actually what I'm showing you here is the last decade. The x-axis is going from 2008 to 2022. The y-axis is the energy per instruction going from integer 4-bit to floating point 64. So this is in unit of joules. Okay. You can see that the energy is coming down, but in a given year, the delta in energy between the energy intensive system and the most energy efficient system is more than the delta over 10 years. So these are all machine learning accelerators. We only use the AI and machine learning. Now, if you add the top 500 supercomputers, the energy even goes higher. Because supercomputers are memory intensive, they're used for high-end scientific computations, so they are in.
So how do you read this graph? This shows the spectrum of
so there are breakdowns of this by what architecture, what technology. There's a whole bunch of data all rolled into this. But here the point was, I am probably giving up a little bit of the climax. You can use architecture to get energy efficiency and changing precision of your instruction. Those two knobs give you a lot more energy efficiency than a new technology. That's the model of this. So that's why look at this delta from a supercomputer. So how bad is this? So now I'm showing you the supercomputers. Look at the units, okay? This is 10 to the power minus 13 joules here. There it's about 10 to the power minus 8 joules. I add the transistors to this. These are the transistors. See, the unit just came down. So the transistors are switching very efficient, close to attojoules. But by the time it goes into instruction set, it becomes inefficient. That's exactly interconnect memory, transporting data back.
So is this for a given task, like when you're comparing? Like
No, this is actually used reported numbers.
no, for the delta. Is it for one specific when you change?
No, it is different vendor.
Okay.
It could be Google. One would be a Google. One would be NVIDIA. One would be Intl.
But it depends what operation we're considering, right? Because one operation.
So the operation is given by the color. So if it is blue, all of the things in blue in cross are 4-bit instructions. Blue circles are floating point 32.
So here,
So this is the energy per instruction.
so you're keeping accuracies same to get the same accuracy, or it's the
No, because the accuracy is different, right? Floating point 64 is more accurate than integer 4-bit for real.
If it was a logic unit operation on certain.
So we know how many instructions per second each of these products has, and you know the total power. So this is a top-down estimate. So this is based on reported data. No analysis. We have done no analysis. You will see our analysis later.
So sometimes the reason I was asking is because everyone knows that if you reduce the precision to 6 bits, 8 bits for many of the machine learning tasks, the accuracy of the task doesn't go down. The task, even though the operation accuracy is 64 bits, or so the question here is this spread is normalized to the task accuracy?
No, it's not normalized. These are raw numbers based on top-down. You said what everybody knows. That is actually Turing's award prize of Hennessy and David Patterson. They make a big deal of it in 2020 or 2019. So the religious figures of computer science are only now saying it loudly. Maybe it was implied, and many of you may have known, but it is only coming into the surface now, what it is. And that's not totally true for scientific computation because floating point 64 is needed. And there's a whole discussion on benchmarks, which I have. We can talk about. So now let's take the supercomputers, okay? These are the 2 exascale computers. This one came online just a couple of weeks back in Argonne. This one is in Oak Ridge. These are the powers, 21 megawatts and 60 megawatts. Okay? So this is again based on reported data. These are the top 15 supercomputers. And I'm giving the energy in joules per Rmax. That's a benchmark that's used. This is joules per HPCG. That's a benchmark for high-end scientific computation. So you can see the energy becomes more and more as your computation is more and more convolved. Your benchmarks are different. So now you plot this energy, power that is used per year against the total electricity consumed by the nations. Okay, this is in terawatt hour, total electricity consumed per year. Okay, it's terawatt hour. This is the Afghanistan electricity. The top 500 together consumes more electricity than just the country of Afghanistan. That's okay. You would say, okay, that's not exactly a good sample. But what if all the top 500 supercomputers became exascale computers? Then, if all the top 500 supercomputers became the second biggest exascale computer, the electricity consumed will be more than Israel, Finland, Switzerland. Just the 500 supercomputers. If it becomes as powerful as the 2 exaflop supercomputer, it consumes more electricity than the continent of Australia and about 67% of UK. Just 500 supercomputers. So now if somebody says energy is not a problem, you can see that all the computers are migrating to this. UK cannot host 500 of these supercomputers. That's how bad the problem is. Okay. So now I will kind of switch to why I think I make 2 cases. One is complexity, one is energy, to say computing needs to be re-examined. So one of the things, one of the papers which is not quite referred to is a Turing's 1948 paper. That was the first one which gave me this idea. Turing had said that information processing in biological systems and in man-made systems both can be classified as active versus controlling. Active means the whole system is doing information processing for whatever it's doing. Controlling is you control it to do a certain kind of computation. Then Norbert Wiener, I think Gert mentioned about him briefly. He had said, in addition to that, control is needed in this, and also communication and statistics are involved. So, taking his work from 1948, then von Neumann actually talked about biological systems as computing systems now. Von Neumann tried to estimate energies. And then Shannon gave us the basic unit of information processing. And then finally, David Ma at MIT actually came up with a formal system for doing information processing. So what we did was we combined these 5 pieces of work, and we essentially generalized it, which I'm going to run through a few things, but hopefully it will make logical sense to you. In order to generalize it, you need to define exactly the terms you use, because it's very much defined by that. Algorithms or instructions or laws of processing information. Remember what we are trying to do. We are planning to apply computing to nature and man-made together, whether it computes or not, to address it. And software is the medium in which algorithms are executed. Hardware is the physical substrate, and architecture is the organization of the hardware. If you just buy into these definitions, then we can say that all information processing systems for an application can be thought of as a combination of information processing in a hardware assembled as defined by architecture using algorithms and software. So this definition falls from the previous definitions, actually.
So can you go back one slide?
Sure.
1 second. Go back one slide.
Yeah,
thank you.
So once this is done, now it gets interesting. So then we need to put it together. So logically, you need a logical way of definition. Sorry.
I'm just thinking of something, like when you talk about software, you say, like an example of software is water, but couldn't that also be hardware?
Very good. So I will tell you the definition of software. I carefully chose because people in biology, like Craig Venter and all, is using DNA as software. Is DNA software or hardware? Right. Same point. So the reason water is a software is if I have a given tube, I can either send water through it or oil through it. So I can change the software for a given hardware. That is the loose rationale behind this. Because remember, we want to define water turbulence, we want to define cell, we want to be able to define a whole complex organism, all using the same words. No more new words should be used. That was the base.
In fact, biologists use another term to use wetware.
Wetware, right. You are right.
Can you just expand on that point? Because I guess your point here is that hardware has structure and you can exploit that structure. I guess. Right. So the point for water here would be that there's no structure because you can interchange it with oil.
That's right. Right. But you can equally interchange the hardware for a given software. When you look at it from a physics perspective, they are reversible, but the way we design computers, they are not reversible. Well, they are, because neural network is trying to mimic what the neuromorphic architecture should be doing. So we are doing the same kind of things, we just don't think of it, because intuitively we know that.
Yeah, just to clarify though, you're not saying that water is software, period, but in a given setting, water could be software for that problem, right?
That's right.
Right, so because you could also switch it around, and then use the structural property of water in a different context.
Yes. Right. The reason, as I mentioned, the rationale for this is very simple. If I used to explain turbulence and I explain viral infection, I should be using the same jargon and it should be clear. The reason is when I looked at how biologists are defining it, I saw Craig Venter defines it differently, Richard Dawkins says it differently. So you just don't know what they are calling software is explained in an easier intuitive way. That's why this definition is to make it, put it a little bit more concrete, but it's still an argumentative point. I'm very well aware of that. So then, borrowing the language of computer scientists, we could put a given application, information basis, a hardware and an architecture using some logical elements. AL and SO stands for algorithms and software. And this U represents a logical expression, either E or NE. If it is E, it is using the same thing as the original application. And you will see with examples. If it is NE, you are using a different information basis. Let's say you're trying to do a chemical reaction. If you use a classical bit to simulate it, it would be an NE, because you are not using the original basis of the application. Okay? You will see it more when I show you. So this is application, the same thing. I had it interchanged, but so I just made a last minute change. Architecture should be inside, and then hardware. And then software would be the so-called glues. It could be things like this. Now I'm talking about it just from computing aspect because we understand software much more from computer thing. This is an example of an application as general functions. Informational basis is digital and classical using Boolean logic. Architecture is network-based. Hardware is resistors and capacitors. This is Shannon's thesis. So we just mapped Shannon's thesis on this framework. His master's thesis. And if you look at a simulation of chemical reaction, I told you, we could simulate it on digital and classical using Boolean logic, NAND, von Neumann, CPU or GPU, transistors, resistors, and that's how this are doing. Now I have the logical operation and 4 elements of computing. If I put it together, I will get 8 classes of computing. Let me go from here. When the application and the informational basis and the architecture and hardware are all equivalent, then it is class 7. When you change the architecture alone, hardware alone, it becomes class 6. And then you change the architecture. So there's a logical way. You can actually make it E or NE, and with 4, you will get 8 classes.
Can you be more specific with what you consider equivalent?
So equivalent, so the example is, just as I mentioned, let's take a very simple chemical reaction. I want to simulate on a computer. I go log into a supercomputer and simulate it, right? Chemical reaction happens in quantum physics, right? I converted the whole thing into a Schrodinger equation solution using digital bits. Then the information basis is non-equal, right? If I use the same architecture of the computers as that of a chemical network, then the architecture would be equivalent to the chemistry. If I use the same hardware that the particular reaction is simulating, then it becomes equivalent. So let me say one more thing, you will see it clearly. Class 7 is natural systems, when everything is equivalent nature. Class 0 is our computers, that Turing called control. This is Turing's active, that is Turing's control. So there, everything is non-equivalent because you are using a von Neumann architecture to reduce every problem, or a Turing machine. Turing machine would be a class.
So in this example, if you use like one computer per molecule, you would be in class 2.
So I will show you examples. When I show you examples, it will become clear. Best way is to examples. I mean, the logical framework is good, but unless I start applying, did you have this?
No.
So now I'm going to show you an example of brain and neural network. This is a neural network applied on a classical TPU that is class 0, but the actual brain is class 7. Okay? One example. Now, von Neumann versus neuromorphic architecture. If you use von Neumann architecture, it's class 0. But if I use a neuromorphic architecture for pattern recognition, it becomes class 2. So you will see this hierarchy nicely comes out, translates into energy. But I just want you to see these two examples. So the reason I set out the example is you can see that class 7 is what we are trying to simulate in everything in computers. So as we make approximations and abstractions, we move away to our traditional computers. And all I'm saying is there are a whole host of computing frameworks between the two that have not been thought. That is the point. But we still haven't quantified it. Quantitative. So I sent this paper to a theoretical computer science conference. Just wanted to see what their input was. I got actually very good feedback. They said this would be very good, but it doesn't have theorems because it was a theoretical computer science. So the reviewers didn't like that I did not have any theorems. So they said, but however, coming from theoretical computer science, they said, can you quantify what you are saying? So that's what I'm going to show.
Can you just go back one slide? I don't really understand why you consider architecture and hardware to be not equivalent because of
So I have hardware, remember the definition. If I am using a neuromorphic computer based on real neurons, then the hardware will be equal.
In fact, that's what Cauwenberghs started, right? So then somehow it evolved.
People kind of twisted it up.
That's yes. So the application happened with QiNS. Before neuromorphic systems were mostly analog,
right,
and then afterwards.
That's right. So the analog versus digital. So good brought up. The analog versus digital is the informational basis, right? So neuromorphic. My information basis has changed from analog to digital. I will show you, neuron is neither analog nor digital. That's a different argument. But the informational basis on a neuromorphic computer is not equivalent to the information that's used by the neurons. That's why this NE comes. This NE comes in because the hardware I'm using is on silicon, not neurons and wetware.
But how do you define, for example, in the case of the brain, what its information basis is? Because I mean, one of the big problems is we don't know.
I have a whole example. I will show you the numbers. It'll just boggle your mind how complex the brain is. So then, and for that, I need to. You said what informational processing. In order to do that, I need to quantify it. So I actually introduce a new definition, and there's no other way to quantify this. You will see why this is important, called entropy for translation. And I'm going to explain to this. In fact, all these definitions are already known. There's nothing new. Bits per second is the speed with which transistors switch. Instructions per second is what I showed you, floating point, 64, integer 4, that's instructions per second. What I did here was have asymmetric definitions for natural systems. States per second, I mean, Richard Goldman talks about it in detail, and microstates per second, statistical mechanics, because when you deal with cluster systems. So I have 4 units of processing.
What is the difference between states and microstates?
So for example, you are going from here to Denver. So the state is changing from Telluride to Denver. So one state change. Microstate is all the intermediate stops that I can measure. So quantum, for example, chemistry, I can explain it very well. A chemical reaction happens at the femtosecond scale. But the whole reaction happens at an order of, let's say, microsecond. So the state would be a microsecond. The microstate would be femtosecond. I shouldn't have used microsecond. I confused them. Sorry.
Do you mean that state is stable in a way?
No, state is so you want to go from state 1 to state 2, that is computation. But to go into it, you need some micro state to go through, that's the algorithm.
So it's just a level of abstraction.
And this is the same as instructions and transistors, right? Transistors are switching, but you need an instruction with 10,000 switch chains before you have one instruction happen. You have to get the memory, write it up, read it, all that is happening. It's the equivalent of that on the biological systems. Not biological, physics systems. They don't have to be biological. Now, you can define a translational entropy, that is to go from one to the other. You will see how this ties in. It's a logarithm of information processing in basis 1. The ratio of that to basis I to basis j would be what is called a translational entropy. And the total entropy of computing is the sum of all of them. This has to satisfy certain mathematical conditions for it to be an entropy, and it does. So I will kind of talk to this later. But again, the class 7 system, remember natural system, has a translation entropy of 0. Because you're not translating anything from that system for it to come. So that's a good example. It's the equivalent of the energy it takes for natural systems to do its information processing is the equivalent of 0.8 energy. For those of you, it's the same thing. So now I'm going to show you simulating chemistry on a classical digital computer, how these numbers come out. So this is the fastest known reaction, chemical reaction that has been reported on Earth. It's a proton transfer reactions. It takes 46 femtoseconds. So state is, the reaction takes 46. So 46 femtosecond is the state. So you need faster measurement to do that. And this was reported in 2020, and you see the time there. If I do this calculation based on what this, the net complexity comes out to be 12, computational complexity of this reaction, based on the numbers for this reaction. So I didn't do anything. I just used the definition and the numbers reported in this paper, and you'll get a value of 12. The only calibration you have at this point is 0 means it's a natural system. 12 means it's a little different. So here what I'm saying is if I computed that system using classical computer, then my complexity is 12. So 12 orders, this is base 10, 10 to the power 12, increase in complexity when I simulate a single chemical reaction on a digital computer. So if I plot energy and this translational entropy, this is the chemical reaction class 7. That is the chemistry simulated class 0. So you can see that this has 0 entropy as I told you. And if you actually do it on the computer, you have increase. By the way, the energy to compute is also very high. 10 to the power 4 as opposed to 10 to the power minus 20. The energy of reaction is 10 to the power minus 20 joules. The energy to compute is 10,000 joules.
In this framework, is it different if a chemical reaction is induced or if it happens naturally?
Well, the thing we are looking for is the complexity of the, and I will show you in a quantum case. The next example will explain it. As far as we are concerned, induced versus spontaneous doesn't matter, but the energetics matter. What is the intrinsic, the so-called entanglement complexity? The entanglement entropy, I didn't define this, one didn't define it. So you will hear the word entropy in many ways, but the entanglement entropy is very unique to quantum. And for reactions, quantum systems need entanglement entropy. Classical systems don't, and this is equally valid. So I just showed you digital computing, right? Now I'm going to show you, remember I showed you the supercomputers and the instructions? Same thing plotted on the x-axis now, minimum and maximum. So you will see a min and max. The y-axis is in the unit of energy in joules. This is the thermodynamic limit at 300 Kelvin. This is the minimum energy any system in thermodynamic equilibrium would be subject to. This is a single ATP. So nature is operating. This is the nature's quantum of energy. Nature uses ATP to do processing. And that is actually very close. This is a transistor. It's only 2 orders of magnitude higher than ADP conversion. But once you go to the instructions, they become higher. So how did we go from a 10 to the power minus 20 to 10 to the power 4, which I'm going to show you in the next few slides. The x-axis is temperature. Sorry for this messy units. I did not know how to present it reasonably. I'll think through this. The thermodynamic limit is a little higher than Landau limit. These are 2 distinct quantities. We will talk about it later if there is a time. But this is the limit as a function of temperature. It's a logarithmic plot, so it's just as...
It's not the same as putting a minus limit.
The thermodynamic limit is Boltzmann. The Landau limit multiplies that by a law of 2. It's still a controversial unit.
It's not because of different units of bits versus transfer.
Exactly. So that's why I always go to thermodynamic limit, because it's easier for me to explain. Boltzmann limit that everybody knows, right? Everybody who has learned any physics immediately gets it. So now, this is the ATP energy. This is close to room temperature, about 300 degree Kelvin. This is in Kelvin. This is the single reaction energy quantum that I just showed you, below the ADP to ATP conversion. Now I put a single bit switching, the energy starts going higher. Floating point operations, it goes higher. Chemoformatic, because there's something called a Morgan fingerprint. People work on chemoformatics, use that. Then the energy goes higher. So that is how the energy goes high when we put together systems. We add complexity on top of the unit of information transfer by how we are communicating, writing up the information. Okay? So that's all it says. Increasing energy as information processing is reaching into digital mode. And now when I put floating point 64, it's so high. You see the unit? So that is where all that energy is going. The precision you need, the complexity is needed. So that is the basis. So chemistry is very energy efficient at the elementary level, but the benefits at the computation level is decreasing as we go up in layers. Now I'm going to show, this is a very recent paper, just last month or so. There was a team based out of Netherlands in which they emulated quantum chemistry on a quantum computer. And I'm going to do the analysis like I did for the I want to do the simple reaction first, so you'll get a reasonable feel. So this is their experimental setup. They had an artificial cesium atom, because cesium atom is one of the atoms which is the most electropositive. It transfers energy. Put on top of indium antimony substrate. 42 layers of indium antimony and clusters of cesium atom. So 6 to 8 clusters of cesium atom on indium antimony mimics a single atom. So remember, somebody was asking me, how is the hardware different than the architecture? Now the architecture they are using is similar to the quantum on which the actual reaction is happening.
But it's still more complex than just using.
Right. And the complexity number will come out. You'll see. So, and they used a constant current scanning tunneling microscopy. This was the potential. And I asked them for a lot more information. They couldn't either get it. So I actually made estimates based on their paper. So they actually put mimic that benzene molecule by putting 6 clusters of the cesium on indium. And they looked at the structure. They did it with butadiene. This had 6 cesium atoms. Butadiene had 8 cesium atoms, representing each of the carbon and the hydrogen. So now, how do we estimate its entropy? We know the energy because you know the energy of formation. So if you assume, so now because we are in the quantum domain, we cannot use classical Shannon entropy. We have to go into entanglement entropy. So it is, I assumed a maximal entanglement, total electrons in the emulated system, and using quantum basis and principles to compute quantum chemistry, you end up with 936,000 atoms just to mimic butadiene. One butadiene molecule in their emulation system needs so many electrons. The real butadiene has order of 100. Okay. This is benzene. Benzene we know is C6H6. So 12 atoms. In order to do 12 atoms, they need so many electrons. So you can actually calculate the entangled entropy. They will roughly come to the same to second decimal place because it's a logarithm. Now, let's look at the energy. So you have to look at how much time does it take to scan a single figure. I couldn't get the numbers, so I had the minimum and maximum time. So the energy it took for them to compute must be between 3 times 10 to the power minus 14 joules and 4 times 10 to the power minus 10 joules. Okay. This is the energy that it takes to emit. So I had my friends at Caltech simulate benzene and butadiene using BFD on a digital computer, right? They did it on a quantum emulator. We did it on a digital computer. Look at the energy. Okay. Same one. Now we can do the same plot. So this is the chemical configuration class 7, close to 10 to the power minus 20. This is the formation energy of benzene. This is their emulation class 6. They just moved up one state because they use the same information basis as quantum. Classical computer, you see the energy. So the energy to translational entropy seems to be correlated. They are not monotonic because 0-point energies are different. Now, in some of your minds, you already are probably jumping ahead. Now, if I don't know the energy, I want to reduce the energy, I can design a system for a given entropy, translation entropy to lower the energy by taking class 6, class 5 closer to the real system. And so I have put it all together and you can actually see the numbers, the energy in joules and the translation entropy to base 10. You can use it any base, it doesn't matter. So this part of its summary, depending on the time I will go into it, the rest of it. A new logical framework has been developed which synthesizes Turing's formalism, Turing's original formalism, Wiener's cybernetic for control, von Neumann complexity, Shannon's theory, and Mars abstraction levels. But as I'm working on this, I'm finding out they are starting to tell me a little bit more about how the physical laws are finding the most efficient path. So I'm actually seeing something very elegant under it. Now, this part of it is everything in nature from small virus to gigantic galaxies are all processing information without access to supercomputers and processing maximum information for a given energy, but yet an external condition seem to be the underlying premise. And this framework classifies everything from a Turing machine to a physical system. Energy information is the minimum for active natural systems. Information processing is not free. Even in quantum, you saw that. If I used a different architecture, kept the same informational basis, I still am going up in classes. So then now I can switch to algorithms and software depending on the time, or we can spend some time to discuss.
Yeah, just as a point of information, so it's a fantastic talk. We already had a lot of discussion in between, but we are now at I think already in the coffee break, and we have to be out of here in I think 15 minutes because there's a talk back to 7.
So I can stop right here.
So I think we could have a discussion now. I mean, if people need to get the coffee, do it now. But
there's lots of exciting things in the software.
Yes, so we can do it tomorrow, right?
Yeah.
Yeah, and that's maybe so. Sadas, you have another time slot tomorrow, and we can continue this there. And then maybe we will need to move some of your other stuff, and maybe we'll find a third slot if needed. Yeah.
Right. So anyway, I've titled this kind of beyond strict neuromorphic. So where I see again kind of sweet spot we're going to use for spinning up. I won't bore you with the kind of big overview. I've actually just picked 3 examples, go a bit more in depth. And disclaimer, they are by no means finished. This is kind of a research direction, work in progress. So this is also kind of getting us started. I actually want input on particularly one of those problems. I probably need input again from the QiNS people, from Gregor. We haven't actually talked about that one yet. But again, it's work in progress, so take it with a grain of salt. Right. So I'm preaching to the converted here, but this is kind of the thing, yeah, where I'm going. So what mechanisms fiber should support, how algorithms need to be recast to do this kind of brain-inspired stuff. And brain-inspired stuff, I mean, yeah, first one is of course sparsity. And sparsity doesn't just mean spiking, right? Sparsity means network aiding. If you assume you've got a large language model, you've got something like 10 to 11, 10 to 12 parameters, and basically for every one of those decades, you can probably think of an organizing principle in which you can get sparsity there, right? It's not all this, sorry guys, bottom up, let's stick enough spiking neurons at it. You really need to put an organizing principle at many levels. So that's the thing. Really work on sparsity, use prediction models at various, use information gating, use uncertainty basically. All these kind of things, use attention mechanisms to really gate information, because that's what the brain does, right? And this is what GPUs, what regular large language models, you name it, they don't do it, right? They always work on the full data flow, and this is what makes them inefficient. Then, of course, second thing, you gotta have a hardware that's really energy proportional, which is way harder done actually than said. To quote this main Apple designer of the A1, it's seriously hard to make a chip that's good at doing nothing. Basically, if it's doing nothing, then it doesn't really draw power. You really have to think a lot about what's drawing power in the background. I mean, in analog, it would be all the biases. In digital, it would be whatever, some kind of system intercommunication links that draw power the entire time. So you need to get those down. You need to get communication energy proportional, which is also on an HPC scale, like we're going towards filling up. It's not that easy, because these kind of high performance links, LVDS links, they usually need to be balanced the entire time. So they are good, again, at this data center thing, where you just throw lots of data in continuously, then they're very efficient in terms of energy per bit per distance, but they are very bad if you really have this kind of sparse biological thing where you only transmit a packet, close it down again. So we really designed us in Spinnaker, basically the protocol stack, the kind of algorithm stack in terms of communication, really down to the individual links. We made very sure that they really only draw power when you do something with them. Same goes for the computation, same goes for memory access, of course. So this was one conscious decision, for example, in Spinnaker 2, we went for LPDDR4 interface. Not for high bandwidth memory, like NVIDIA does it, for example, because high bandwidth memory has a lot of baseline power, right? You hardly notice when you access it, which is, again, good for this kind of high throughput, batch-wise processing that you usually do on GPU machines. It's bad if you go neuromorphic. It's bad if you go for sparsity. LPDDR4 scales a lot better in terms of energy per memory access. Right.
Where is that coming from?
Come again?
The statement now that there's no under limit.
Yeah,
you're going to talk about it.
Exactly. Relevant question. So let's put it like that. At least make the upper limit a lot weaker, because that's another thing we can take from biology. We go partially asynchronous. And again, I don't necessarily mean that to mean it's AR and it's all this handshaking. It means on a system level, you can have streams of information going across the machine, which are at least somewhat independent, which have usually under limit means you can parallelize processes arbitrarily because you get data dependencies, you get synchronization dependencies. So one part of the process has to wait for another part. So basically you cannot spread it out as much as you'd like to. And if you take this inspiration from homology, again, at many levels up to system level, that you can essentially have processes run but either trivially independent of each other, or at least in a fashion that they integrate the information when it comes in real time, instead of waiting for one another, right? So that's the next thing that goes actually hand in hand with that. You can have, also like Gordachi does it, you can have locally dense computation. You can have CNN stages that are very dense if you do it locally. But globally, communication really has to die off with kind of proportion. Otherwise, you always start a communication there. Even if you're laser pass and everything, you still run into bandwidth problems. So you also need to kind of think how your topology really is.
Sorry,
yeah.
You asked me why was TP? Why was TP?
Come again? Locally dense you can do. Of course, if you're locally sparse, it's also good. But globally sparse you have to be. Globally sparse you have to be. Otherwise, the problem doesn't scale up. If you're not globally sparse, if you don't have a distance-dependent die-off of communication in your computation task, then basically you will just be bandwidth limited, right? So again, you cannot spread out your task as much as you'd like to. Right. Okay. Anyways, I won't bother you with that one because it's just a big. This is just to give you an impression of what it looks like in Dresden at the moment. So yeah, that's the server rack. So we're getting there. Current status, you know it, that the single boards are over there in the lab. The 48 node boards, the first ones from testing, they're getting back in August. And we will set up, so that's kind of a half-size machine, 8 server racks, 5 million cores, will be set up until the end of this year. So that's when we really scale up. And of course, in the meantime, we try to seriously build up a software stack across the startups, the Spin Cloud systems, and across the chair, essentially. And this is, one mean machine. It has been, especially during Corona, the supply chains were rubbish. You had to really grab the components as they were coming in, not order them in bulk, but like we needed several tens of thousands of them. Like these easy converters for the boards, you really had to stat my PhDs at the suppliers. There's 100 available again. Let's grab them. There's another 100, right? That was supply chain issue. So yeah, it took some serious manpower to get this thing done. Still does, of course. All right, so let's start right now. First example is kind of tying together an AI stack. Full stack, I have a summary slide, interim slummers right later on, that really goes towards the advantage of the machine. So the first thing here is we're going, so this is what we call eGRU. We had this on ICML, ICLR, and NeurIPS plus last year. The thing is, very much like RNNs, because they usually take less effort and they also a little bit bio-inspired, right? You integrate information across time. It's not that you can integrate fire neuron, but it also helps you with time dependency. So it's a seriously cool thing, especially for time series. If you want whatever, audio coming in, video coming in, you can do a lot of stuff with recurrent units. The problem with regular current units, they're of course fairly dense actually, especially in recurrency, it's even worse than the feed-forward architecture usually. Kind of information tends to build on each other and then you get all this dense communication between the individual units. So what we did at the individual GRU unit, but also at kind of, so it's a network of networks topology, also at kind of sub-networks of GRUs, we're building in something like a neuron threshold. So we're basically thresholding either on amplitude coming out of this GRU unit, or we also have a second stream where we compute the uncertainty that the local network has about its decision. And we basically either threshold on the pure amplitude, or we threshold on that the network is certain about what some decision it has reached. And then we feed forward it. So this kind of stuff actually gives us a quite high degree of sparsity, again, at multiple levels, because you can do this trick not just at individual units. So this is, again, something a little bit like biology. You really hard code it, and so you reset it as well. So you really do a threshold, and you're transmitting not just a spike, you're basically transmitting the entire information of the GRU, so it's basically a vector, or for population code also be a matrix, and then you're resetting internally and start integrating information again. So you can think of this GRU unit as kind of like a neuron on steroids, integrating multi-dimensional information, thresholding it, passing it on. So it's really
Christian.
Yeah.
It would be nice to contrast this with the delta RNN, you know. What's different about this than the delta RNN that we showed back like 6 or 7 years ago? Basically also it has exactly a GRU, it has temporal sparsity exactly like that.
I would need to look at the specifics. I mean, definitely this is mostly ex-grants, guys, David Kappel and Anand Subramani, and in the paper they contrasted it with the delta RNN. I think with the delta RNN, they had it in there, so contrasting their own approach. So it's definitely there in the paper. Actually, Matthias, you want to chime in?
Yeah, so the main difference is that in the delta RNN, you work on the difference of two successive values, right?
Two successive inputs, yeah.
And here, this one directly works on the values and only,
So I think it goes out to higher level sparsity actually than the delta RNN.
I don't understand the difference. Basically, the only difference is unit by unit asynchronous.
Yeah, but you've got this reset mechanisms which you don't have in the delta RNN, right? You really integrate. It's more like you're integrating upwards, then you transmit and you reset again. It's not just kind of delta encoding the output and just pushing on the deltas. So this is I mean, you can configure a neuron that it does delta encoding, but usually you configure a neuron that it integrates, punches the information on, and then resets it again, right?
I don't understand the functional difference though.
Yeah, in this case, it's really a little bit like it was like spiking.
But you know, if that was a delta RNN, it's also spiking in the same way. It's just that it happens to be clocked.
Well, but the delta RNN doesn't have some kind of reset mechanism in this way.
But you don't need to. We purposely leave it out because we want to transmit the information through the network without loss.
The point is this more general than it?
I would say it's more general, yes.
Then you can also reduce it to.
You can reduce this to a delta RNN, but the intent is not just to encode the delta between two time steps. The intent here is really to integrate information across longer time spans, reach a decision, and then pass that information on. So it's operating on a kind of higher level of processing.
I still don't understand. Anyway, we discuss it later.
Yeah, let's do this offline. Yeah.
So what do you feed back into GRU? Is it spikes or is it the membrane? Kind of memory potential, I guess.
It's kind of the memory potential. Actually, the inside is still very much a GRU unit. So inside again, it's not spiking. It's the usual GRU, so just time steps basically. So again, this is like Spinnaker, where globally asynchronous. So this is kind of the globally, right? You go asynchronous across the other networks, internally and sparse. So that's asynchronous sparse from here. Internally, we can be synchronous and we can be dense. So that's the internal part, basically, running on the single cores. And up from here, it's basically core to core.
So what is going out of the cell is spikes, but inside the cell it's...
Exactly, yeah. So you can think of it as being inside the neuron, we have continuous values, continuous time kind of thing. Yeah.
So what comes out are events that are enriched with more information.
Yes, yeah. So we actually, in a number of ways, so we transmit the internal state of the GRU unit, and we can also transmit, if we have this uncertainty measure going, we can also transmit the uncertainty to the upper levels, which the automotive guys find seriously interesting, because then you really get from the substages, you basically get a measure that the network usually is kind of regular output of resonant or whatever is kind of artificially secure, right? It's always 1 or 0 because you've got this nonlinearity. Here we're actually transmitting how secure you really are about something, and the higher levels can then base their decision on that again.
So what microarchitectural units do you have in Skinnaker that allows you to do it efficiently?
Come again, Andreas.
What is the hardware architecture that makes it well suited for Skinnaker 2 as opposed to something else?
I mean, of course, so the question was what's in the hardware architecture of Spinnaker that makes this model yes. Run good. Now, I'm just repeating it for the guys here because they don't get the audio, the remote ones. So I would say, of course, you can run this on a GPU, but the GPU again doesn't have this kind of energy proportional external link, so it doesn't really give you a lot if you go for sparsity. When you run this on a GPU, you hardly care about the thresholding. You might as well run it like that. On Spinnaker, this one really gives you an energy advantage, and actually also partially a time advantage, because you use your MAC units in the subsequent networks way more efficiently. You only ever activate them when something new comes in.
But I wasn't talking about GPU. I was just talking about it's just a microcontroller. It might
No, it's, I mean, the individual kind of kernel, the processing element in Spinnaker has, of course, this Mac accelerator. It can do nonlinearities, all this kind of stuff. So again, it's, yeah, you're playing to the strengths of Spinnaker in the sense that you can do DNN, RNN type processing locally, but you don't want to do it on a global scale like a GPU does it. On a global scale, you want to go kind of neuromorphic, gated, etc. So that's how it plays to the strengths of Spinnaker 2. It's like a GPU at the local scale, but we try to use the GPU very efficiently in the sense that basically we only ever activate when something comes in. And at the global scale, we try to go this kind of external sparse in a sense.
Yeah, this thing is implemented as C code within the ARM core, right?
Yes and no. So the nonlinearities, so the matrix operations and the vector and whatnot operations, they work on the Mac array, and part of the nonlinearities are also implemented in the Mac array. Only if you need a very complex nonlinearity do we go to the ARM core, and the ARM core handles kind of a data flow in between.
I see. So really what you're using here is the vector unit associated with every core.
Yeah.
How many? It's one every core.
No, it's one in every core. It's a 16 by 4 8-bit, but can also configure.
No, but you have one on every core.
Yes.
A vector unit.
Yeah.
Okay.
So you really think of this as an extension to a leaky integrated binary that has a lot more internal dynamics?
Yes, yeah, that's actually how I think of it. Yeah.
And the main difference with another neural processor is that the events coming out are then enriched as opposed to binary. And how much do you gain? So if you were to output just the binary events, the threshold, I mean, the event itself as opposed to the line, how much would you lose?
We actually didn't investigate that. I can quote you a paper from Chris Elias. They actually tried, but that is of course the neural engineering framework again, not quite this year. And they said the sweet spot was around 4 bits. So that gave you the kind of least energy to transmit information across a given line in a sense, and the most expressiveness in the network. So you don't need floating point that you're transmitting here. But on the other hand, 1-bit information is not quite the sweet spot.
So more
and it's also a question of, it's not just a question of efficiency. Again, if you have this uncertainty measure locally and you can transmit that on about your decisions, then it's just added functionality, because this is a seriously cool, I mean, of course, you can do this easily on GPU as well, but the automotive guys have a real problem getting their stuff functional and safe, right? And they have a real problem with usual data, whatever architectures, being very artificially sure, even though their stuff is very outside the training range, basically. I'm actually coming back to that point later. Okay, yeah.
Quick clarification. So the Y is this like Y is on average typically like 4 bits, or it's a vector of 4-bit entries? And if it's a vector, how big is this vector that you would send this event? Like on the output of this.
Okay,
it's in the different stream.
I think in this implementation it's 8-bit. We went with the 8-bit because it's a native kind of format for Spinnaker internally. And it's a stream, yeah, it's not an event.
Okay, so
okay, there's more I want to show you actually. Because I spent the whole time on this slide. But there's 3 papers on this out there from last year, so you can look up the details. And anyways, this is only partially my work. I started this whole thing with 8-bit, and then with Anand, he took it to completely new heights and he moved off to Bochum. So yeah, we started this when he was a postdoc in my lab. Right. So yeah, just to give you a bit of an example here of this is a DVS gesture recognition. And this one here, okay, you don't see it, but this is the state of the art kind of data augmentation plus CNN plus whatever else. It takes about 600 million effective meg per, I don't know what the normalized time was there. I mean, the same stuff for hours. So EGRU plus data augmentation, everything. And we get a factor 1 to 60. So this is really what the sparsity gains you, way less computation per unit of time. Of course, picking an example that's seriously good, but we usually fall in a range between factor 10 and factor 60. So somewhere along there, this is the level of sparsity you're getting at virtually the same performance, right? This is a trick. So with that kind of stuff, we won't outperform the regular machine learning, right? I've given up on that. I actually tried that. But we will get, if we take these kind of principles in there, we will get way more efficient at the same kind of performance. So that's the game I'm in. Right, so just one numerical example, what we're getting there. Okay, that's the next thing. David has tried to make learning more efficient. And you know, all these kind of approaches like forward, random feedback alignment, all this kind of stuff. Now, this is a kind of new take on some of those things. And I'm giving you the conclusion beforehand. We actually trained this on 30 or 40 teams in certain neural networks, which is usually where these local learning approaches tend to break down, right? You usually only get 6 to 10 layers. So that's the seriously cool thing about this. Otherwise, it is computationally a bit simpler, but it's really that we can do kind of local learning basically across many layers. So how we do it? That's the kind of first step. You all know it. This is an autoencoder, right? So we had this actually in the board yesterday, I think, from someone else. So you start with the full image, you've got a bottleneck layer across several stages, and you expand it again. What's kind of new about this autoencoder specifically, it doesn't just autoencode and compress and decompress the image across this bottleneck layer. It actually, so that's where the uncertainty comes in, it tries to, in a second stream, so that's the sigmas here, it tries to also judge where it's uncertain about the image content. So across the bottleneck layer, tries to figure out where it's essentially where it doesn't know what it's reconstructing. And the funny part about this, so this is fashion MNIST, actually works quite well. It was kind of surprising. You see here, there's this whatever characters here on this shirt, and it can't really reconstruct the characters. This is the error basically that it's making between that and that image, and this is what predicts where its highest uncertainty is. So it really learned to say, I am uncertain about the reconstruction of that particular part of the image. So that's the first part of the magic. So this autoencoder, and then you actually forward the autoencoder. So essentially, when you have a regular kind of visual processing chain, you have something like a bottleneck layer. You always have a larger space at the input, and you have something like your class layer at the output, which is the stuff actually getting end-to-end trained. So you can think of this whole chain, if you add a second one that kind of decompresses it again, then you've got this autoencoder again, right? We folded the autoencoder along the bottleneck layer. And the interesting thing is, with the uncertainties, so we're now only computing the uncertainties here. The uncertainties we can use as local loss in the individual layers. So it's not as computationally efficient as some of the local learning rules where you only do this, like EPROC, for example, where you only do these very coarse kind of feedbacks. We're doing actually very fine-grained feedback. But the advantage is we basically need to do only a single inference pass, right, for the backdrop, compute very detailed uncertainties for the individual weights here, and then use those across these subnetworks. So it's not, you're taking basically every 3-4 layers of subnetwork, and then use the uncertainty that we got for the subnetwork to do local backdrop. So
what's the local backdrop on? What's your target for that local backdrop?
The local backdrop is basically reducing the uncertainty.
Reducing the uncertainty.
Yes. Yeah. So it's going along the, so it's backpropagating, or backpropagating is not the right term. It's feeding the uncertainty via this kind of, again, it's like an inference feed forward path into the individual subnetworks. This is the uncertainty. And the local backdrop tries to minimize the uncertainty.
By following a gradient.
By following a gradient, because I mean, every time step, you get a different uncertainty, right? And that's the gradient that gets minimized by the backdrop across the local network.
So, Christian,
yeah.
So what do you use to this is what we want to do, something similar, this training that you just described.
Yeah.
So what do you compute? What is your metrics? Quality metric that you decide how to really backdrop on that. Yes,
it's again, I have to pass this one off to David. This is his stuff. It's he tries to explain it to me, and I basically lost it at equation 5. But it's a probabilistic uncertainty measure that's based on Kullback-Leibler diversity.
Okay, because like the previous example, something like an entropy measure.
It is something, yeah, it's something like an entropy measure, yeah.
Thanks.
It's actually fairly simple, so it's hugely complicated math, but at the end, it's a fairly simple expression.
Okay.
So it's some probabilistic entropy does. So again, in terms of computation, this is not necessarily completely fitted to Spinnaker, but in terms of general computation, right, you only need to do a single inference pass. And then you only need to store kind of the information for backprop across the local network and only be guided by that thing, right? So that's the advantage for that. We're still trying to get in sparsity as well. So this is not sparse at the moment. This is kind of a second stream to the one I showed you on the last slide. We need to get those two together in the end. That's why I'm saying this is work in progress very much. We're trying to build all these different building blocks. The EGIU was mostly for inference, actually, getting the sparsity. This one is getting the computation and especially also the communication and the storage down for learning. And now we need to make the sparse as well, because yeah, also for training, for Spinnaker, sparsity gives you something, right? Because it really makes, you're using your units, basically, your computational units more efficiently. Maybe one more thing that this also gives you, if you only do backpropagation across the local networks, you have way less of a problem with a vanishing gradient. So that basically means we can fixed point backpropagation. We don't need floating point precision here. So that's another advantage. We're getting numerically way simpler by only doing the backprop locally. Because so this stuff is fixed precision, right? This whole feed backward network. And then the backprop is also fixed precision. So we're totally getting by without floating point precision in this type of learning. And yeah, we also did a vanilla transform of that in the latest paper. And yeah, just to give you an example, so it's quite on par with backpropagation. Also, this what we call the block local learning. So yeah, again, accuracy-wise, we can train really deep networks on par with backpropagation. And as I said, get by, for example, with just integer resolution instead of floating point resolution. Yeah.
In what kind of application do you see the interest to having a sparse and low energy training? Because usually it's a step that we only do once and then deploy it. Then you don't care as much as energy efficiency.
You do care.
I know.
Because I mean, my example would be for example, for large language models, we talked to a company that does that for some kind of chain of legal offices for their research purposes. And this is employment law, and that gets new regulation just about every 3-4 months. So we actually need to retrain that model. Those guys need to retrain the model quite often. So we care both kind of inference efficiency, energy efficiency, as well as training efficiency. And of course, in the wider context, if you look at the resources that OpenAI threw at large language model processing, yes, you do it only once, but if you have to burn something like 1,000 A100s for 6 months, right? And here you get less of that energy, maybe even less time, because you're doing it more efficiently than that, because floating points also take more time, right? Instead of fixed point operation. And that definitely also then scales your effort you have, right? But Toby, what would you example? Okay.
Quick question, because on the slide before you were saying local backprop, but are you actually really backpropating anything, or are you just you have a local loss and you do gradient descent on the local loss, but you don't really backpropagate?
You have no. It's in that sense, it's a local backprop, right? You have a local loss for the output of that subnetwork, and then you do regular backprop across those 3-4 local layers.
Okay, across these 3 layers.
Yeah.
Oh, I see.
Okay, to give it even a higher spin, we've started working on symbolic AI, integrating that. In this particular instance, we're working on what's called NARS, non-axiomatic reasoning system. That's an our invention. This is by Wang at Temple University who did that thing. And it's way above what I usually do. So I also have a bit of problem getting my head around it. It's almost philosophical, but in essence, it's a mathematical concept. So you guys are kind of familiar with symbolic AI. So in this case, it's a formal language for knowledge representation where you basically have a set of rules and a set of databases that you're basically training to represent higher level concepts, to represent, let's say there is this example here. So you get from lower stages. So this system is interesting because it works off DNN input. So you can get events. Events would be this guy here as a high-level entity being recognized and walking somewhere. And then basically the reasoning system, the NARS on top, tries to reason, yeah, this is an entity of class pedestrian, and it's supposed to behave like that and that, for example. And that's what it's trying to acquire. So it's trying to acquire kind of behaviors of objects here and how they interact.
What does that mean? What is axiomatic? I don't know what axiomatic means. I don't know what it means non-axiomatic. What's axiomatic?
I talked to Paivang about this at length, and I think it's actually axiomatic in the sense that he defines axioms that then make up his reasoning system. So axioms really, in this case, and I don't know why he calls it non-axiomatic. We've had a long discussion. But in essence, what axiom here means is really you have the standard set of inference rules, basically. And they get combined in different ways during training. That a pedestrian can have a vector moving like that, or he can do a random walk or whatever. That's what the system acquires based on the baseline rules, right? So it has a set of baseline rules that you set, and then it tries to construct behavior of objects out of those baseline rules in a sense. So that's the axioms kind of. So it is fuzzy logic, but it also goes in the direction of what Chris does with the what's it called? Remind me, guys. The vector symbolic architecture. So this also means you can link objects and do combined behaviors for objects, for example, how they behave, how they relate to each other, what's the probability of having object A in the image of object B is in the image, this kind of stuff. So it's not just fuzzy logic. It links it actually as it's pretty multi-layer. Yeah. So you basically have you are constructing the whole image, what behaves in there, for example, with this individual objects, then this group of objects and how they behave to each other. So it's this kind of very hierarchical thing as well. So that's what NARS does. It's cool in the sense that it's also, we're doing a big defense project now that you instantly detect anomalies. So again, this is like this earlier example. It's not like a DNN. This is that's artificially simple, even though basically the new stuff coming in is way outside what it has been trained for. With this system, you very reliably detect anomalies. The stuff that has not been trained basically pops up essentially. And then you've got a choice. You can basically analyze like we're doing with this defense project, you can analyze what this anomaly is. Is it a technical defect? Is it someone attacking your network or whatever? Or you can also incorporate that, of course, in your learning. So the learning in the system can both be kind of guided. So you can actually set rules as a human, like expert knowledge, and then start training on top of that, have it acquire new rules. So and because it's a symbolic system, it's way lower dimensional than your usual deep neural network, right? It's on top of the deep neural network. So that also means the rule sets are still kind of human readable, human tractable. So that's the cool thing about this. It kind of condenses this very complex processing that goes on in the DNN, in essence, in rules that are still kind of reproducible, where you can say, this is why the system does what it does. Right? So the system itself, it starts on very low primitives. So it's not doing your usual deep neural network, but basically the whole decision comes out. Yes, I want to take an avoidance decision or whatever. You're really kind of constructing the deep neural network more for individual primitives, like recognizing a pedestrian, and then anti-reasoning, like giving the pedestrian a trajectory, having it interact with other objects. That's no longer part of the DNN. That's part of the symbolic stage then. So that's the idea, and you have almost like, and it's actually it's kind of neat because it's event based. So you're really thinking for the symbolic AI, you're thinking of events, something new in the image. Okay, I'm always going image, but these guys, Paivang and Patrick Hammer, they're doing this. They're also working on language models with symbolic AI. You think about stuff moving into the symbolic layer as an event, so it's actually fairly sparse. And you've got these reasoning agents that integrate part of the events of your deep neural network. So each reasoning agent has access to the whole rule set, but it only reasons about part of the image. And they've got this network of reasoning agents that also communicate very sparsely and interact until they kind of reach a final decision with the top level kind of integrator node of the symbolic AI. So again, it's not really neuromorphic, it's more neuromorphic at a psychological level kind of thing. So at this high level of processing, but it's neuromorphic in the sense that it's independent processes, or let's say processes that are asynchronous at least, in the sense of their interaction, and it's very sparse, it's easy parallelizable. So that's also what makes us very interested in Spinnaker doing this. And the other thing is you have a hard time, so that goes back to Andreas' question, why specifically Spinnaker? Because Patrick Hammer, who does a lot of that at KTH Stockholm, has a hard time mapping that to GPUs. Those reasoning agents have quite complex C routines. You can't parallelize them on a GPU. So the thing that we have in Spinnaker, where we basically do this, the DNN stage in the Mac accelerators, and then in the ARM cores kind of do this rule-based stuff, which is just regular C code, this inference, is actually seriously cool that we have this very fine-grained CPU plus GPU functionality. Yeah?
Why? Two questions. One is energy efficient operation compared to what?
In this case, compared again to a GPU or HPC version of this.
So have you done the number?
Not yet. That's kind of, you think exactly. Yeah. So this is for the future. We actually don't have a large implementation yet on Spinnaker, so we're working on that. Once there, we benchmark it against the GPUs. Yeah, that's work in progress. Yeah. Right. Yeah. Anyways, I won't bore you with that side. So this is what I think we tie together, right? It's this sparse coding plus this kind of DNN functionality plus the symbolic AI layer on top, which makes it seriously cool. Which actually is kind of what DARPA says third wave of AI. So getting the efficiency out of bioexploration, getting this real-world data handling of QiNS, and getting the reproducibility and the secureness out of symbolic AI. So kind of combining all these different streams together again. So this is what I find really cool about this. Yeah, anyways. Yeah, we have nice workshops on that. So let's try a different take. So we had this is kind of the AI framework that I'm trying to build up, these different streams and unify. This is non-AI compute. So again, what could be our advantage? Something like Spinnaker on non-AI compute. So we have extreme parallelism of simple operations, right? We are ridiculously parallel compared to an HPC machine. HPC machines usually have 100,000 cores. We've got 10 million cores, and if you take synaptic updates, you're actually getting to 10 to the 14 synaptic updates per millisecond. So you can ridiculously parallel stuff. So if you map numerical problems to something again that conforms to this, like we had in the beginning, that's partly asynchronous, where communication lies off the distance. You can just throw it at the torus, like we discussed in the QiNS group. For the optimization problems, you just throw it at it and just ridiculously parallelize it to get it. For example, if you have a hard time real-time constraint, like we have in this one optimization problem, you just get the time scale up, way up compared to HPC. We also, of course, do have those stochastic accelerators in the course, way more than you usually get out of software and HPC. So you can do also, again, Boltzmann machines, you name it, Monte Carlo models. That's also where I kind of think that we're going with the machine on these problems. Anyways, yeah. Sorry, yeah.
10 to the 25 quantum entanglements. How do you define that?
I talk to the physics guys, and it's basically if you've got the quantum entanglement space that blows up with the number of qubits. So this is if you had something like a 200-bit ideal qubit, so not the physical qubits you have at the moment, which of course have way less entanglements, but about a 200 qubit ideal qubit machine would have something like a 10 to the 25 dimension entanglement matrix behind it.
With no noise, right?
Yes, of course. If it's noise.
So I also don't understand where that number came from.
I talked to the physics guys. They gave me that. That's what the number comes from. I actually had a paper. I can send you the paper. Right. I'm actually not sure if we're going to do this one. Yeah, well, let's do this one because actually I want to get your guys' input on offline. We can discuss about this. So yeah, let's do this one. It's cool.
If this works, then the NSA will be after us, right?
Yeah. Well, they will buy the machine. That's what I'm after. Of course. So again, semi-prime factorization. So what's the usual stuff you do in the quadratic sieve or number field sieve? You start out with a Fermat factorization. So you basically want to factorize n, which is the product of two large primes. You start out with this x squared minus y squared equals n, which then the factorization, the trivial one, gives you x minus y times x plus y. And you're trying to find this x and y. The first step you're doing is you're kind of making the search a bit easier by going mod n. So that's the same kind of expression. It just gives you more chances of hitting the right x and y. And then, of course, you can slightly transfer it. So that's x squared equals y squared mod n. So you can do a bit of funny math there. Then if you have x and y like that, then of course, I mean, those still have mod n in there. So to really get at the factors, you have to do the greatest common divisor of x plus y and x minus y. So you need to get rid of the mod n again for the factors. So that's part of the math. Then it's still not quite easy. So this is the step actually where the Shor algorithm steps off. Shor algorithm tries to find them. It converts this to a period search because you're looking for the zero crossings of that equation, and does a quantum Fourier transform and basically tries to find the 0 point of that equation directly. In regular supercomputing, you do it a bit different. You're not looking for x squared equals y squared. You're trying to find x squared equals y mod n. And you're trying to find a number of those, basically. So number of the y's that will conform to this, because then you can basically combine them. So if you have a number, if you have a couple of those factors that kind of go together like this on this factor base, then of course this is not yet a square, right? It's y, but it's not a y squared. But then you can kind of multiply, because of the mod n, you can multiply those equations on both sides. And you find a number of those where you then kind of can combine them to actually have something like 2 to the 2, 3 to the 4, whatever. So this becomes a square in the end. So that's the kind of idea again. You're looking for numbers like those y numbers that conform to that equation, and that basically are composed. They call it smooth. They're composed of multiplication of small prime powers, basically. So that's the idea. Then what the quadratic sieve or the number field sieve do is they have construction polynomials which have a high chance of hitting basically a y that is both smooth and conforms to that equation up there. So that's the basic trick behind a number field sieve. There's a bit of math involved. You get a constructed polynomial, again, that fulfills that equation and is smooth. And the usual way you're then parallelizing, so in number field sieve, you actually have a number of those constructed polynomials. So you've got actually a three-dimensional problem. So you're trying to, what comes out of this constructed polynomial has a fairly high chance of hitting a smooth number, but it's still very sparse. So you're searching a huge number space for these smooth numbers. So you need to basically parallelize the search. So you get the generated polynomial, you generate all those numbers, and then you basically have this huge three-dimensional space. So basically, polynomial is one axis. The range of that individual polynomial, the numbers you generate, is another one, and the factor base is another one. So you've got this three-dimensional kind of search space there, and in that you're looking for the smooth numbers. And one interesting thing is that actually standard high performance computing can at the moment only parallelize across the polynomials, the number of polynomials, and the range of the polynomials. It doesn't parallelize across the factor base. And there is a neat paper out from, actually I had the reference in there. Yeah, anyways. So that's a paper out for doing neuromorphic prime factorization, and they're using all this machinery out of the regular kind of quadratic sieve in this case, because that's all not the hard part. The hard part, really, the one that scales exponentially, that makes it hard to factorize number, is this inner part, this smooth search. And they figured out a way to do a neural network, so that's tonic spiking neurons plus a couple of weights, in which you actually parallelize across the factor base. So they call it the third dimension, basically, right? So this is already seriously cool. So now we cannot just parallelize across the polynomials and across the range of the polynomials. We can also factorize across the factor, we can parallelize across the factor base. They haven't quite figured it out yet, because they then go serial basically across the range of the polynomial. But right now, what we're trying to do together with them, actually pretty close, I think, to basically use just this part of the parallelization and take this part of the parallelization across the polynomial from the ordinary methods. So then we really have this kind of three-dimensional space, yeah?
You're about 5 minutes into my class.
Okay, sorry. Okay. Anyway, so the inner part, there is, let's finish with that one here, and let's forget about the other example. The inner part of this p-smooth search is still a laborious process, right? Now we've potentially factorized it across, parallelized it across all three axes, but it's still a very sparse search. Now there is various methods, you see it, yeah, it's QiNS again, it's icing, it's whatever, that you can increase the probability of actually hitting a p-smooth number in that search space. So you're not going parallelized across all three axes, kind of across the entire space. You're actually kind of subdividing the space. So this is something we haven't yet figured out. There is a number of ways to do this, but it's not yet plugged into these other methods. So this is actually something we could then take offline and also discuss it with the QiNS group a bit. Anyways, yeah, I get you, Andre. I need to finish up. So I will, that's the summary, but I already told you that. So there's all the reference also in there. And I will completely not go across our quantum emulation. I don't have time for that. But it's also very neat. I can take this offline with you, how we do the decision diagrams in Spinnaker. Yeah.
You can have another time slot in QiNS.
Maybe that, yeah. So anyways, that's my team in Dresden, and yeah, you know, it's connect with Spinnaker, and it will be multiple Spinnakers, right? We're talking to just about every HPC center, and we're actually close to doing a couple of contracts with Sandia, Oak Ridge, etc., setting up the machines, so Spinnaker will become widely available to the entire community here.
Yeah.
So you're with me on the Fermat factorization, right? That's just this x minus y times x plus y equals m. So you're going to find x and y that fulfills this condition. Then you've got your n factorized. Basically, your x minus y is then one of those big prime factors, and x plus y is the other big prime factor. And the reason people do it is because you can do this mod n in this way, right? You can basically do mod n, and the n just basically goes away, and you have x squared equals y squared, right? Get rid of that n. This is one reason why they do this reformulation. But then, of course, if you find x's and y's, you have to do again this greatest common divisor, because you need to get rid of the multiples of n. And again, Dixon factorization adds one on top of that. We're no longer you're looking for this one here, we're looking for this one here basically. So it's like, yeah, I don't have an example here. But again, the idea is you fulfill this equation, right? So you assume, you're actually assuming that basically you're taking the square root of n, and you are choosing an x that is somewhere an integer value around the square root of n. So you're basically assuming that those two factors are about equal size, the semi-prime ones. So that's how you come up with a couple of trials for x. You just kind of use a couple of values around the square root of n. And then you try to find y's that fulfill this equation, right? So for that given x value, find a y that is p-smooth. So that's basically can be just broken down in these very small prime factors, and that fulfills this mod n equation. So that's the idea. So you're with me though, so far, right? And then you go all the way back. If you have, so the last part is basically then, if you have y's, a number of y's that divide like that, then you find some way of multiplicatively combining them. So let's assume there is one factor that has this distribution, and the other one ideally has a distribution where there's a 2 in there, a 5 in there, and a 7 in there, right? And then you multiply the two, and then you get basically a combined factor that's 2 to the 2, 3 to the 2, 5 to the 4, and 7 squared, 7 to the 2. And then you basically have a square. So you can start, you're doing several of the y's until you find a construction for a square here, and then you basically back to this step here.
So you have a y1 and a y2, and you multiply them, but then you get x cubed. No?
Yeah, but the trick is the mod n.
Yeah.
You can easily cube that because you're just getting rid of the cubes with the mod n if you do the math. I did that really on a paper. It was surprising even to me. You get rid of a lot of this of this whole cubing. You get rid by this trick with the mod n. Because it doesn't, you don't care how many times the n you've got in there, as long as you do the greatest common denominator divisor, then you're back on square one, and this is actually quite easily doable numerically. So that's linear time on a regular compute machine. The hard part is then finding the b-smooth basically. So stuff that divides like that, and that fulfills that equation up here. So that's why, again, something like the number field sieve or the quadratic sieve, they take this equation here and they work out a constructor polynomial which fulfills at least that equation here, right? So they basically they have a constructor polynomial that they also again give a range of input, like they're counting through whatever 0 to 10. In that one example, it's like in a second, it's yeah. Here, so the x is the input to this constructor polynomial in this simple case, and the fx is the output of the constructor polynomial. So you have, I don't have the equation here, but the fx is constructed in a way that it, that it fulfills this equation here. And what people say is when you do the constructor polynomial in a certain way, it doesn't just fulfill the equation here, it also has a high chance of being divisible, basically. But high chance of being divisible still means, if you look at this example here, we've got this constructor polynomial. There is actually, yeah, here it's almost half. It's like, what is it? 8. Come again. That's 10. Yeah. So 4 out of 10 are b-smooth here. Of those numbers you build with a constructor polynomial, which is quite high hit, but then you only get on the small factor base. So usually this factor base doesn't just go to factor 5, right? You actually need to go to whatever for large numbers. You easily have a 77 here as a prime number, and that way, basically hitting enough of them that this number is very likely to be a smooth number becomes a lot sparser. So again, the idea is you've got this factor base that you're assuming that the b-smooth numbers are based on. You've got the generator polynomial. So you're building up this space. In this case, it's 2D. And the third dimension is different constructor polynomials, right? So that would add more of those matrices here. And a usual high performance computing basically fills all this in parallel in a vector. And in the other dimension, fills multiple of those vectors with different constructor polynomials. And then you basically go with this usual kind of sieve of Eratosthenes, this kind of stuff, where you do serially go through the prime factors and check if that particular number in that vector can be divided, can be completely divided and be smooth.
To be honest, I don't quite understand the picture here. Could you explain?
Yeah, so that picture is already this neuromorphic realization, but it, yeah, okay, then let's talk about the neuromorphic realization. So again, you're getting that we need to kind of divide the number. We need to check if it's b-smooth, right? We need to check if the 2s, the 3s, and whatever are in there sufficiently enough that it explains basically the size of the number. This is basically what this pattern matching here does in a sense, right? You check if there is enough, let's say single 3s or 3 squares or whatever in, that when you multiply it up again, you are close to, with a certain threshold, close to the original number, which basically means you assume that that number is completely divisible by those factors you found, right? So it actually is a pattern matching problem in a sense. And again, here, this is coming out of this constructor polynomial. So you have this polynomial, you run a certain, so it has a parameter x, and you just, so that's again, there is some mass that goes into how large range parameter x you run in this polynomial that has again to do with this kind of size of the factor that you're trying to find. And then you run this x in the polynomial. This is the output of the polynomial, and that's what you need to check. So again, it's a 2D matrix. You have in one line, you've got the outcome of the constructor polynomial, which is guaranteed to fulfill that equation. And now you need to check if that thing also fulfills the condition that is divisible by these small factors. So that's this 2 by 2 matrix.
But when this where is the y in that? Like, you have the constructor, what does it do? Like
the y in essence is the f of x here. The y in this case is the outcome of the constructor polynomial, because that is the y that needs to then go into this equation.
And so those the kind of numbers, but you have here numbers going from, for the other x, from -100 to 100.
Yeah,
it's the range.
That's a very small factorization here. You also have to say, right, because it's also a very small factor base.
In general, what would be a realistic number there?
Again, it is a function of square root of big N, what you're doing here, because it's like, again, for the x you're going for square of the big N. Okay, that's a typo. It's also big N here. You're going here for square of big N, and this one is also related to the square of the big N, because that's about the size you need to explore, kind of.
And the big N is?
Big N is the number you actually want to factorize.
But what I see, okay, but that can be enormous.
Yeah, of course. I mean, we're talking about, again, if you have an 800-bit encryption, then this big N is 800 bits wide, yeah.
Yes.
Yeah. And right now, with, again, number field sieve on a really big HPC machine, there's a number of French guys who do that every year. Takes about 4 or 5 months to factor 800-bit number with all those tricks built in.
So 800-bit number would be a good benchmark for us to.
Oh yes, yeah. I mean, actually, this stuff here, the guys who did it, they did it on True North, and they had a problem. Yeah, I'll explain that in a second. The thing is, you need fairly large fan-in, especially in this first step. You see here all these connections; those are inhibitory ones, those are excitatory ones. And with a larger factor base going to realistic numbers, that fan-in actually becomes quite large, and they were limited by this 256 fan-in that True North can do. Yeah, so that's why they didn't tackle anything bigger. So I think they factorized up to about 200-bit numbers.
I see. Do you have a reference to the True North?
Yes, I actually do. It should be on the slide here. I think it's in the here. It's here on the next page. No, that's one of the post-quantum things. It's really hidden. One second.
It's okay. It's fine. You give us these slides.
No, I'm gonna. For some reason, it's.
Oh, it's there. It's there.
Yeah, exactly. That's a reference. It is on the slide. It's just hidden.
And what's the superscripts and the subscripts? Just a notation convincing it. So you have 2 sub 3 sub 0, and so.
Okay, bear with me. These. So this. Okay. Yeah. So the superscripts are the powers, right? So this is really 3 to the 3rd. So that's how often basically that factor is contained. You see it in 27, right? Actually, that's a hit here, and those are the inhibitory couplings, right? It's also finding the 3 to the power 2 and 3 to the power 0, 3 to the power 1. But it's basically those are the inhibitory connections over here, so that it will only basically notify that it's found this 3 to the power 3. That's the kind of highest power that it found in there. Yeah, you don't want to double count, exactly, because in the end, that's what these logarithmic weights here do. You sum it up again. And again, this is what I try to explain to you. You're trying to match up if the factors you found in there account for the entire number in a sense, right? So here it's adding, but it's adding logarithmic. So that's basically like multiplying the original value, right? So you're adding up the prime factors you found and looking if it really accounts for the entire number.
And what does the gray mean?
Again, the gray means it has also found those factors, so 3 to the 1 or 3 to the power 2 inside that number, but the highest one, the 3 to the power 3, is the deciding one.
I see.
And the subscript, the lower one is?
Yeah, the subscript is the phase basically. You see that here they do it as tonic spiking neurons. So again, look at this one here, for example. 3 to the power 1, subscript 0 is phase 0 starts initially. Spikes here, spikes here, spikes here, spikes here, right? It's just a tonic spiking neuron with a period of 3 starts with phase 0. And this other one here starts with phase 2. So again, you can generate that on an ordinary compute machine, those phases and the periods quite easily. It has something to do with the constructor polynomial. You know, given the constructor polynomial, when you start at a certain point with this axis here, you know that some of those factors need to be there at certain phase relations when you go through the constructor polynomial.
So we should actually think of this as really the t is an actual time axis, like it's
yes. In this case, it is an actual time axis. So this is the output neuron in time step n. That's this neuron here, and this is basically this neuron here, tonic spiking with a period 2 and phase 0. That's the next one. So these are really the tonic spiking neurons at the uppermost layer, and then. Again, they tonic spike. You see basically from the phase when something is supposed to be part of that number, checks for the highest, adds it up, and then sees with its threshold in the output here, and sees basically if that can account for the entire value of x in the constructor polynomial. Sorry, f of x. Yeah.
So I had a question before on this.
Yeah.
These log 2, log 3, where are they coming from?
They are coming from that again. This neuron here basically checks. Yes, there is a 3 to the power 2 somewhere in there.
3 to the power 2 somewhere.
Yeah. Then you're running in time through the constructor polynomial here, right? You do all those values, and you want to check. Is it divisible by those factors? And when you do the right phases and the right periods, then basically this becomes the spike pattern here. And the spike pattern from the tonic spiking neurons, you need to check, is there a 2 in here? That's over here. Is there a 3 in here? Is there 9 in here? Is there 27 in that? And that's why you need the logarithmic factors, because in the end, you want to again, it's you converted a multiplication. Actually, you would need to multiply the prime factors that it found up to see if that accounts for this f of x, right? So in this case, for example, 30 would be you found a 5, you found a 3, you found a 2. So that means 5 times 3 times 2 gives you the 30. And you don't do it multiplicatively, you do it with those neurons additively. And that's where those logarithmic weights come in.
So the logarithmic weights means it's equivalent that you must have that many layers in a binary tree, right?
I'm not quite getting that one.
So what does log 2 mean? Specifically, log 2 means you have a bit of information.
No, don't think of it that way. It's not, this is really, it's the factors, right? And you want to check if adding up all the factors that it has found accounts for the whole number, accounts for this whole f of x. And you don't do it by multiplying, you do it by adding it up in that neuron. And that's why you need to add the logarithms of those factors.
So S of t is the log of the number you want.
Exactly, yeah. You threshold S of t with the log of that number.
So, but sorry. So that means it is very dependent on your basis set. Yes, chosen log 2, log 3, log 3.
Yeah, of course. Again, you have this network will always be 3 layers deep, and you just extend it to that. Say you've got factor 7 in there, you've got factors 13 in there. You also need to take all those different powers of CF7, powers of 13 up to the size that the maximum of the f of x can be. Of course, you don't want to. It doesn't make sense to go for higher powers of 7, for example. And then you just construct it again with the subjugatory couplings, with the excitatory ones, and with a log 7 or log 13 for the summing here.
And just so when you are the inputs to this basically you're generating different patterns, right?
Exactly. Those are tonic spike nodes. They don't have an input. Yeah. They are just I spike with a period of 2 with a phase of 0. Period. Done.
Yeah. Okay. And the phase offset, that's the subscript, and the value itself is equal to the period, and the superscript is the
power of
this factor. Yeah.
Exactly.
So the question is the width of this layer.
By the way, not quite. This is not the period. This is the period, right? This actually has a period of 9. See, it only spikes once in that whole interval.
Oh, that's why. That's the sure Hopland who's producing.
So this only spikes every 27. Of course, with a phase of 0, so it spikes once here and it would spike way over there again.
Okay, so maybe the third row would be a good example. So the third row you would fire every 3 times, yes. But it's inhibited there.
Yeah, here, for example.
Okay, and then the fourth row you would fire every 9, but it's cut off because
you don't need the full range because it doesn't make sense for that factorization to go with your polynomial beyond that range that's defined by this minus x to x.
But in a sense, that is just brute forcing, isn't it?
This is brute forcing it, yes. No, the whole algorithm, again, this whole number field of quadratic sieve is brute forcing it.
Yeah.
You're constructing a huge room and you're looking, you know that the numbers in that room, again, conform at least to this equation here, plus have a certain chance of being B-smooth. But it's actually very sparse. You're looking for kind of very seldom candidates inside that room. And that's why you definitely for the brute force, again, ordinary high performance computing, usually parallelize along that axis. It just generates all those f of x in one go, and then actually goes serially with a serial sieve, tries to factorize it again, single one if that's B-smooth, plus ordinary high performance computing parallelizing this axis along the different constructor polynomials, so constructing more of these matrices basically. And what those guys in the Neuromorphic paper have done, actually, guys, I need my batteries going down. So what the guys in this Neuromorphic factorization have done, they've actually turned around the time and the time in the parallel axis. So again, ordinary high performance computing. Parallelizes here, goes serial here. They parallelize it here and goes serial through time along that axis. And what we're trying to do at the moment is actually combine those two concepts, right? That we get this 3-dimensional parallelization, which can be done. I mean, trivially, you just think of you chunk this in, because this is a very long axis actually, you sub-chunk it, right? You start multiple networks that just have the same period, but different phase offsets. And one network just sends those 4 numbers. The next one just sends those 4 numbers, basically.
Going to talk about a topic that Gert and I presented at this ISCAS 2023, which and a joint session with ISIT, the International Symposium on Information Theory, and it's introducing this concept of learning in memory. So why are we talking about this in the QiNS group? In the morning, Sadas, he gave an excellent talk about the notion of physics of computing. And so this talk also ties very well with the same theme, talking about fundamental energy efficiency limits, classical quantum and quantum inspired. So we were thinking that we will open up this another theme as a part of the work group to investigate these fundamental limits. So that's one of the reasons that we're going to present some of the results and approaches how we can actually do that. So the topic of optimization is not only relevant to QiNS, but it's also relevant to the overall theme of AI training. So here is a graph that I'm showing that shows several interesting trends. Okay, so on the x-axis are the number of parameters in state-of-the-art machine learning models. I'm showing GPT-4 over there. And then how many flop does it take to train a GPT-4, PaLM, DALL-E, GPT-3, right? The colored dots are showing the results from academia versus results from industry. So one trend you see is that as the number of parameters have increased, academia has dropped out. Right? So most of the new results, everything, the training, they're essentially coming from industry. And why is that? Mainly because the computational costs have gone to a certain point that academia can't even afford to run these training algorithms. So that's one thing that's happening, which is bad, which means that there are not many different, I would say, groups that can verify what GPT-4 was trained on the data that we can't verify, right? So that poses a security risk. And that's where I feel that we should be moving towards democratizing AI training. So as more people train with different sets of data, you can make some of these systems more reliable and trustworthy. Right? So that's one trend that you see. The other trend that you see is one plot, which shows, so this is a log-log plot. So this initial trend shows that the number of operations that you need to train some of these systems, this scales quadratically with respect to the parameters. Okay? Which makes sense because if you're training, you have to do pairwise comparison, like quadratic optimization. So the training complexity should kind of scale with this, with the square of the parameters. But then if you look at the newer trends, like how GPT-4 and PaLM, that's trending, that scaling looks more like linear with respect to the parameters. Okay. Why do you think that is? And I'm going to conjecture. I also don't know the answer to that. So
I think it is probably more marginal.
Okay.
What repeat the statement?
Okay, so if you look at the trend, the initial trend when the parameter size was small, like a small machine learning parameters, the trend was quadratic with respect to the parameters, the number of operations that you need, right? But if you look at the newer models, like the transformer models and other stuff, the trend looks a little bit linear with respect to the number of
because they retrain.
So these are all speculations. One is
they don't start from scratch.
Yeah, so mainly they are doing model adaptation. Yes, so they have a pre-trained model and all, and because training from scratch is prohibitively very expensive. Okay, yes.
No, you're right on the dot. This is the same kind of a curve like the frequency curve I showed, right? It goes high and then it starts to taper off because the resources are so intensive in terms of power, energy, and compute.
Yes.
And the other thing which I hadn't thought about, which you just brought out, is since the academy are dropping out, these are done by the number of models that are able to handle trillion type parameters are very few.
Yes.
Okay.
Yes. 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 So you can. So that trend is telling you that the power of AI training is getting concentrated amongst the few. So that's what's also happening. This trend is showing. So the reason is why this is useful is that ideally we would like to get to about 10 to the power of 15 parameters, right? Why? Because that's typically the number of synapses in the human brain. And what would it take to train a system as big as that? So if I assume the optimistic case, which is like a linear trend is going to continue, I extrapolate this, that will take about 10 to the power of 27 flops. Okay? So to understand what does it mean to do 10 to the power of 27 flops, so I'm going to take some of the numbers of the state-of-the-art systems. On a 1 TOPS per watt GPU, which is a nominal GPU, it will take about 1 petajoule, okay, which again means it's equivalent to the energy dissipated in a large city. That's the energy consumption. Or if I take the state of the art, and this has not been achieved yet, if I take a compute in memory system or with a density of about 100 TOPS per millimeter square, it would take about 300,000 years to kind of train this. Okay. Or if I take a wafer scale system with the same density, this is Cerebras. Again, Cerebras has not achieved this density yet. It will take 8 years to train a system like this. Okay. So this is what it's showing that this at least the path we are on is not scalable. It's not sustainable. something has to happen, something has to change. Questions?
Yes, my colleagues at Jay should tell me that they can train new domain on a GPT-3 like model or an NVIDIA rack, 100, about $450,000 kind of compute server in a few hours.
Yes, so they're using pre-trained models. They are using a pre-trained model.
Yes, yeah, exactly. Use adaptation techniques.
Yes. So if you do that, but what we are saying, if you do things from scratch,
but nobody will do things from scratch. And
there is a reason why nobody wants to do things from scratch. One is this cost, and the second thing is that there are certain problems, like the folding problem. I think what you mentioned, where the data you may not be translatable. So the problem set, you have to train that from scratch, train things from scratch. Right. So yes, if you do model adaptation, you can get away with things, but then you also inherit the problems too, what the original model was trained on. What is the objective? So that's partly the motivation for this talk. What are the bottlenecks associated with AI training? And everyone knows that it's memory and network. Right? So it's not compute. That's the problem. And not only for AI training, but for large-scale optimization. So things which we are trying to do in QiNS, when we are solving combinatorial optimization, yes, when we have our variable size is big, we can't keep everything in memory. Maybe Spinnaker can do it, but there you have to swap in and out the data from memory. And then what we are going to say, and we are going to propose this paradigm of learning in memory, and argue and look at what are the fundamental limits associated with this paradigm. Okay, so yes.
So something on, there's a very nice build-up. The learning in memory has different variations depending on who you talk to. You probably know this better than I do. That how close you are to memory computation. So you may not actually compute in memory. But you're more closer than you are now. Right?
So I'm going to talk about that.
Okay, so that itself is not, as far as I know, well studied.
Yes. So that's what I'm going to talk about. And we are looking at more fundamental limits, and then maybe discuss what would be the pathway to a practical realization.
Okay, but that actually, just to, I have one slide I can show, but I can also tell you just without showing it there. The problem is not really the memory problem. The problem is going to memory hierarchy, and that is, it's clear what the challenges there are. Yes. And we do have fixed numbers for the pilogers to really go, for example, surprise you probably, you think a register file of a computer unit, the register file, it may be better than a L1 cache because it's closer. But actually the cost energy to go to the register file of your processor is about 10 amplitudes per bit. Yeah. To go to L1 is 8 because L1 is more condensed memory. The design is smaller, so the cost. So it's all about distance.
Can I say something?
Yeah, please go ahead.
So, I agree with that first premise, but memory is not that efficient either. So depending on what level of memory you are talking about, it gets not just the distance, which is I agree with that point, but the memory itself. The memory itself at L1 cache or even to L2 or to DRAM. They get also there's an energy penalty because they are all on the order of 10 to the power minus 12 to 10 to the power minus 15 joules.
Right, and I understand that that's exactly what we have in our papers, but no, but it's the memory itself, if done right, doesn't consume energy.
Well,
it's really access to the memory that actually consumes energy.
Yeah, so it's access to the memory.
So not really the cell itself, yes. We can discuss that. I mean, but that's
So typically, we feel that there are three bottlenecks associated with memory access. One is the memory wall that a lot of us know, like update wall and consolidation. So just to recap, what is memory wall? It's essentially how often you access memory. You have to bring data, you're right, you have to bring data from memory, compute, and then store the data back. Okay, it's the energy efficiency bottleneck due to memory transfers and swaps. And for that, industry and academia, they have followed this compute in memory paradigm. In fact, compute in memory paradigm came from this community. Like in its neuromorphic nature, synapses, and is localized along with the neuron. So yes, there's a compute in memory solution. But for training, there is this update wall limitation too. And the update wall comes from that you not only have to read the data, but you have to also write. Right? You have to write. And for training, the precision that you need for many training tasks is much higher than what you need for inference. So inference, you can get away with 6 bits, 8 bits. But for training, you generally have to at least have 12 bits. And for scientific computation, it can go all the way to 64 bits. Okay? So that is one of the major bottlenecks for training as well. And then the last one is the consolidation wall. And this goes back to the memory hierarchy. That when you are accessing memory, because you have limited memory capacity on certain locations, register, cache, you have to keep storing memory at a distant location. Okay? So bringing memory back from different hierarchy dissipates power. And in fact, training and optimization is a little bit different from the conventional compute cycle, because anyone who has worked with optimizers, they know that the variables that are important, okay, they are the ones that you have to keep in the closer to the compute cycle, because those are the parameters that change very fast and more often. Okay? Whereas the parameters which consolidate early enough that you have to store far away, or that you can store far away, but those are important. Okay? Because those parameters you can't forget. So you have to keep accessing those parameters that consolidated early. Okay, whereas you have to keep the parameters that keep updating closer to memory. So there is a kind of a trade-off here between the memory hierarchy and the dynamics of the optimization process. So there are these three bottlenecks. Okay? And what we are saying is that we can address these two bottlenecks, the update wall and consolidation wall, along with the compute memory, using this learning in memory paradigm. Okay, so I'm going to talk about this a little bit, what this paradigm means.
The reason you picked up these two as opposed to compute in memory is already mainstream type, while these two have not been studied.
Yes, so compute, exactly. So compute, there are many different topologies and architectures that actually a lot of us in the room, we work on this, integrating this with memristors and space state memory. So yeah, there are lots of different, but there are challenges associated with it. But everyone acknowledges, yes, you have to bring compute and memory together. That's not new. So what we are saying is that, okay, you have to look at the other paradigm, which is now you have to learn in memory as well, not only just compute. And what does it mean? Okay. So that's where I'm going to talk about this paradigm and then discuss the fundamental limits. Okay. So before I talk about that, I will make some assumptions and abstractions. So remember, this is a talk where we are going to, since we are talking about fundamental limits, I'm going to make some abstractions. The first thing is, we will say that optimization will involve, that there are some parameters which we will call weights. The weights have to be updated at a certain rate, or this is equivalent to updating the memory. And while you are, optimizing or training, there is a loss function associated with something that keeps on monotonically decreasing. Now, of course, you can argue it may not monotonically decrease, but at least we can assume that the overall learning trend will look like this, that some loss function metric has to go down. Okay? So initially, during the training phase, okay, what we are defining this training phase is where this update rate or this function, the loss function, keeps decreasing. And then when the loss function has stabilized up to a certain value, we say that, okay, the system has entered into an inference. Okay? So that's the first assumption that we make. It's a reasonable assumption. And then the second thing we will assume is an abstract memory model. Yeah, this is nothing new. This is a physical memory model. It says that, okay, there are two memory states, okay, state 1 and state 2. They will be physically separated by an energy barrier. Okay? And you have to choose an energy barrier large enough such that these two states don't leak. Okay? So typically this height of the energy barrier is determined by the thermodynamics, leakage. Okay? So generally for memory systems that has to keep things for a long period of time, this barrier is about like 100 that you have to choose. Okay, so this is the one assumption that I would make. Yes.
Assuming they're not close enough for tunneling.
Yes. So I'm assuming that there is no tunneling between the states. So now with this, let's first look at the thermodynamics of limits, and maybe Sadas, you might this might be the topic that you may have wanted to discuss, but I will kind of talk about this a little bit. So what is the fundamental limit of this? And that comes from Landauer's limit, and everyone knows, we'll just refresh what Landauer's limit is. Okay. It essentially arises because of second law of thermodynamics, which says that the change, whenever you have an entropy change, okay, it's equivalently associated with a change in energy, right? The energy has to be dissipated. Okay, so this is a very simple description now of the second law of thermodynamics.
Yeah, but can we argue or disagree? Can we argue?
No, I'm not saying, I'm saying this is the definition. And what we are saying is that. Yeah.
I guess that's how we argue. Yes, we are.
Yeah.
That assumes equilibrium.
Exactly. Exactly. No, I'm getting there. I'm getting there.
Because there's no limit.
Yes.
Right. There's no equilibrium. I mean, this is really Pamela's work where it's simulated. The stochastic differential equation you can compute.
Yes.
That's 1 picovert.
Yes.
If you wait for 100 million years.
Yeah, exactly. So, and this is again, remember, this is a recap for folks who are not familiar with Landauer limit. So, where does the limit come from? So, if I reduce the state of the memory model to just 1 electron, so we are working with only 1 electron, and I want to move this electron from this state to that potential one, which means that I'm transitioning this from 0 state to 1 state. The way I have to do this is that first I have to lower the energy barrier. Okay. Yeah. And as soon as I lower the energy barrier, what happens? Before I knew the electron was exactly at this location, right? As soon as I reach this state, now the electron can be in 2 locations. Okay, so now I have increased the uncertainty where the electrons can be. Right? So as soon as I have done that, okay, I will dissipate this energy, and this dissipation comes because of erasure. Previously, I had a perfect knowledge of where the electron is. Okay, so once I dissipate this energy, which is kT log of 2y2, because initially the electron was in 1 state, then now it can be in 2 possible states. Right, so that's where you get this, metric, and this is per bit. Okay, not max. So,
and the other way of thinking about this, without those arguments, in a very intuitive fashion, is you have an energy barrier there.
Yes.
But there's thermal energy. Get this, right? And the barrier to be at least as high as the thermal.
But that kind of, so I will show. So once you have this state, which means that the electron can be in both states, then what you can do, you can apply a small potential difference between the two, small enough that the electron slowly drifts from this location to this location, small enough. Okay, and that's where the equilibrium part comes in. That if you wait long enough, this electron will asymptotically reach this state, and then once it reaches this state, I will increase the barrier back again. Okay, but note that yes. Okay. So again, if I use this simple amount of bit and I multiply it by 10 to the power 27, assuming a 16-bit as a floating point operation, I will end with this. But again, this is not a practical limit. But the problem with this is that this process is adiabatic, which means that you have to wait for a long period of time before the electron actually shows up. And then the second thing is, this assumes that the energy that I kind of used to move the barrier, I can recycle it back. Okay, and that's a very big assumption. Many times when you charge a capacitor, you cannot recover the energy back. So the energy recovery is a very big assumption here. Okay, so 2 assumptions there. So this is not a practical limit.
Adiabatic there means it's very slow.
Very slow, yeah. Any questions? Okay. So what about non-Landauer fundamentals, right? So if you assume that we are ready to dissipate the energy that we put in moving the barrier up and down, So let's say now instead of using one electron, we have many electrons that we are working with. Okay? Because single electron can leak out, a lot of practical issues might show up. And what we will do is that we will literally push all these electrons up. Okay, and then we will push them over the barrier. Okay, so they end up in the other potential well, and then I will increase the barrier, right? So where is the energy dissipation here? Okay, the energy dissipated here is that I'm kind of pushing the energy profile of all the electrons, imparting some kinetic energy, and then I'm dissipating that kinetic energy away. Why? Because I need to do something in this state. Okay, whether I have to compute gradients, for example, and all those things we have to do. So we have to stop this process to actually make something useful. Okay? So if you look at, like, again, going back to the assumption that we have this energy minimization process, or we are reducing the loss function, it means that every time we are making a weight update, parameter update, you have to repeat this operation over and over again. You have to stop the computation, calculate the gradient, and then determine how to update the next weight. Okay, and you have to repeat it multiple times. So each cycle, you have to dissipate this much amount of energy. Okay? From actually how good your memory is. Okay, how efficiently you can update the memory. So I've chosen a number which is about, for 1 bit, 1 femtojoule. There are more efficient memories than this, but 1 femtojoule is good enough. Okay? So if I use this practical number, and again go back to 10 to the power 27, I'm getting close to like terajoules and things like that. Okay? And remember, this I haven't taken into account the complexity of gradient calculation, communications, all those things I haven't taken. This is simply just memory updates.
But how do you get a number?
So this is, let's say I've taken like a resistor. Yeah, 10 to the power. So there are autojoules per bit memories too, but
so that's not fundamental, but it's practical.
Yeah, it's a practical limit.
Right. And so to really change the state is really because to really access that bit, again, it's communication.
Yes. Or so remember, so the reason what I wanted to articulate here, what did we do here? We kind of accelerated these electrons and then we dissipated the power there. Because we have to stop the electrons. We have to kind of stop the computation at each step to do something next, right? So we can make the measurement of the state so that we can calculate the gradient. So what I'm going to argue next, which is the learning in memory, is rather than dissipating that energy, we start with an energy profile that looks like this, okay? Where all the electrons, we are kind of pushing them. But as they are accelerating along a certain path, we start modulating the barrier. Okay? So we start increasing the barrier. Yeah.
In this argument, unless the electrons are decoupled from any physical system or are absolute zero, some of the electrons, even if there is a drift there, because it's going to be small, but some of them are going to go back by
exactly, and that's what when we talk about fundamental limits, we will talk about that. How do we make sure what is the trade-off between how should this slope be? Okay, so the forward is much larger than the reverse leakage, and how should we modulate the barrier? Because the barrier is going to control how many electrons can actually move from this state to this state.
So sometimes, if I made a statement,
yes,
that this looks like the gate potential of a transistor.
Yes.
Do you not agree that this looks very similar to that?
Yeah. So this could be the source, drain, source if you want. And this is the gate. Exactly. No, exactly.
Get us into this classical physics is at the limit of that, we can see today in flash memory. Moving an electron from the left to the right is going to be inhibited by the electrostatic potential of that well there. So, and that's why we see these single electron devices, leakers, make a lifetime about it, where you can see single devices moving, you can count single electrons going left to right, and there's a jump.
Yes.
So I think there's another effect which you don't include, which is really the electrostatics of that well on the right side.
Yes, so all we are doing here is all here we are doing is that we are not limiting to single. We are saying, okay, send a bunch of electrons. All we are saying is that by moving the energy barrier, we are reducing the probability or the rate of flow of electron from this end to this. We are applying brakes here.
Yes. There's a cartoon picture, but Shankar will show. We'll get the nuts and bolts.
Yeah, meaning there we'll go through the derivation.
So we can do single electron learning.
Yes, you could. In principle, you could. In principle, you could. So the idea here is that, okay, initially we start with no energy barrier, practically no energy. So all the electrons kind of rush through. Okay, and then as we are reducing the loss function, we apply brakes by modulating the barrier. Okay, and such that the states of the electron end up at the right spot at the right time. The challenge here is how do we modulate the barrier such that not all the electrons gush through very fast. Okay, so we want to slow it down gracefully. Okay, right. So we have to kind of modulate the barrier in the right way. Okay.
Can I say something?
Yes.
So this is, I understand what you're saying. If you make it slower than the phonon frequency, you are going to be having an equal flux coming on the other side.
Yes.
Due to scattering.
Yeah, due to scattering, due to leakage. Exactly. Yes.
That is one. Then the second thing is, I probably missed something. You touched upon something fundamentally. The difference between the gate and that is how much potential gradient you put in.
Yes.
So you don't want to waste all the kinetic energy.
Yes, exactly.
You want to reduce the waste of kinetic energy. Is that fair?
Yes, exactly. So here I'm not stopping the electrons. So in the previous scale, I moved the electrons and I had to dissipate the kinetic energy. Then apply. It's like going down the hill, but you have bumps. And then you have to apply kinetic energy to go over the hump. Here, what we're saying is that, okay, if you know the profile of the going down the hill, you apply the right amount of brakes at the right time. So you end up at the ground state in this case by just moving the energy barrier up. Okay. So the challenge is how do we match this barrier?
How is energy dissipated?
Yeah, so we will talk. So when we derive it, you will see the energy is still dissipated by this initial value that you apply to all the electrons. And you're still dissipating all of them at the end. And so what we will see, and if I give you a preview, is that this will end up being equivalent to the revised Landau limit, that you're dissipating only the initial energy that you put in for all the electrons, and you're dissipating it gracefully.
Just as a number, my estimate for 10 nanometer technology is about 700 electrons go through the channel.
Yes.
That's the number. So there is a lot of margin, is my argument.
Yeah.
No, but so then, if that's the case, I would take 1,000. Then my noise is about 30 electrons, and so I cannot say anything in this model beyond 30. The equivalent of 30 electron charge current, and that tells me what is my learning precision.
Yes, exactly. So if you don't require to measure in the intermediate state, then we can talk about the fun. But if you have to measure, then yes, you are limited by KTC noise. Like how much, with what accuracy can you figure out where the state of these electrons are?
KTC noise at from equilibrium. You can have devices that have less than KTC noise. People show that. I think it's better to think in terms of short noise, which is really the more fundamental.
So there'll be a lot of variability but initially for learning, we haven't addressed this at all, but this would be a great point to further elaborate on. for good generalization, we actually need noise in the learning process.
Yes.
And so as long as you still have an accurate way of measuring your metric, and there's not injected in or imposed, as long as you still have a good metric.
It's fundamental because the device is sitting at some level.
Yeah, so we need noise anyway.
Yes, so here you are exploiting that noise. So just to tell you, like, what does it mean? So if I So let's say, if I look at a standard optimization process, like learning, I want to get to this final optimal point. I follow a single path of trajectory of updates of the weights. Yeah, and that is determined algorithmically. The algorithm tells me how do I need to update the weights. So I have only no flexibility in updating the weights. Now, if I start from here, like this state, it means that the weights, because there is no barrier, the electrons can diffuse in many different directions, right? So what this paradigm is telling you, there are many different options that it can take. It doesn't need to follow one trajectory to the final track. As long as there is this gradient potential that is there to direct these different paths to the final state. Okay? So we need to make sure that we can maintain this gradient potential for all these paths to converge. So the idea here is that initially the entropy of the paths or possible states, it increases, but then because of the gradient potential, it kind of pushes it back to the optimal lower potential. Right? So we are using noise in this case. Actually,
I understand. You did the similar progress.
Yes. So we are using the same devices. Yeah.
No. So I know it will be the target, so I had time to think about all this. So, but I think what's interesting is that you could do a similar thing and learning using a single electron at a time.
Yes.
And I think that would be really interesting to really explore.
Yes.
The thing that is, because it goes like 1 over per rotor, and also
right.
When you decrease the electrons too much, your statistics will not help permit. The statistics will have to come in timing, not at the same time.
In time or in space.
Like the ergodic thing, you just need to do it in time.
Right. Yes. And so that is. No, I mean, I'm just arguing about direction. I mean,
yes, absolutely.
No, I mean,
so that's one of the work groups in this QiNS project. Like, we want to explore that path and try to argue, like, hey, if we go down to that single electron limit, how much energy will we actually receive practically?
But then you get to the effect, which is a globe blockade.
Yes.
Which is later as globe blockade, where you really your image, charge image doesn't allow you to go and get the globe. Okay, so I think it would be interesting for us as a group to really revisit that whole thing,
Put it on some solid ground.
Yeah, and really relate to the kinds of things that we were talking about. I think the guy really deserves a Nobel Prize in physics. I mean, the only reason he's not going to get it is because he argues too much.
Who is this?
Licker.
Oh, yeah. Licker.
We were there 2 times at the other side. I said, you are there, and I was there, and it was just, will you do one proposal in one day?
So here,
One small thing, which I'm sure you are probably going to get to, when the electron number goes down, there should also be a time constant.
Yes.
So because you cannot get the time out of this.
Exactly. So you have to make sure that the dynamics of this process matches what your training algorithm requires. Exactly. So, and it may happen that in this practical, you may have to inject external energy because some of these paths may start drifting away, because if this rate at which the electron drifts is faster than when it can come back. It's like phonons. Yeah. So if it can overshoot the potential work. So you want that there is an external energy that brings all those paths back so it can converge to the final solution. So that's equivalent to error correction, that you're error correcting the paths so you can make the path converge to the final solution.
But so that demon now that for Lenz, you need a machinery to do that.
Yes, exactly. So you have to either inject energy, at certain points in time, But at least what we are talking about, because we are talking about fundamental limits, we say that, okay, there is no external energy that is injected. The gradient is perfectly aligned, so all the paths kind of converge. So that's where this fundamental limit derivation is coming. But keeping in mind, this is not always practical. You may have to inject energy externally. Okay, so now we will look at how do we design, how do we derive the relation. So first key relationship, and this is more details are there in the paper, is this trade-off between the speed at which the computation proceeds forward and the height of the barrier, right? So one can see here, and the details are there in the paper. If you apply a large potential difference between this and this, of course, more electrons are going to move in the forward direction, right? And then the height of the barrier controls how many electrons actually also move back and also move forward, both distance.
And so what is the fundamental difference between neuromorphic systems as we design it and biology? Because in biology, that is a description of the chemical reactions.
Exactly.
Yes, yes.
And that's a transition.
So that's the transition. That's the transition. And that happens at the molecular level, and there's nobody to control it, and you're controlled by the dynamics of the molecules and all that. Yes. And we don't have that in electronics.
Right. And I
mean, you can mimic that, right?
I know, but then that's $1 million question. After finishing the talk, I'm going to ask you, how big is, well, I gave it up already. Okay, so what was this? Well, no, I mean, how the circuit is, yeah, big. Yes, more.
Yes, exactly.
So one particular concept to build on what you just said is, if it's a transition state, you showed your learning as a fully convex surface.
Yes.
You can actually have hyperbolic surfaces.
Yes.
Also.
Yes, exactly. So I'm going to talk, that's where the different trade-offs come in.
Okay.
But the first is the trade-off between speed and energy barrier, and this kind of tells you the relationship between the two. E0 in this case is the height of the barrier. That delta En is the potential difference that is applied between these two wells. Okay. And then in this case, R max is the maximum rate at which the electrons can move forward, and Rn is the nominal rate at which you are computing. Okay. So what I can do if I plot this, okay, so again, I haven't gone into the derivation of this, you get this curve for different values of this delta E, the barrier height, and the rate at which the computation proceeds. This is normalized with respect to R max. Okay. So you get all these different curves, and then the idea here is here.
And to be clear, so the horizontal axis relates to the learning gradient?
Yes, so this axis where the barrier height is 0, what we are saying is that there is no barrier here. So when we are applying delta E, when it's increasing, it means that we are applying more gradient. There is no barrier. Okay, so delta E, the barrier height is 0 in this case.
That's what
whereas on this axis, there is no gradient between the two potential wells, and all we are doing is just increasing the barrier height. Okay, so this axis is talking about retention of the memory. Once we have learned something, the height of the barrier prevents the state from going back and forth. Okay, so this axis is retention, this axis is speed or energy gradient. You can look at this. Any type of learning algorithm or computation or optimization essentially has to meet these two criteria. First, asymptotically, as n number of cycles goes to infinity, we want the computation to stop. We want R to go to 0. Okay, so the computation has to stop.
So just to go back to the analogy, if you don't mind, just broaden the discussion with the chemical system. So in the context of your discussion here, look, in chemistry, learning is taking two compounds and creating a third compound. That is learning.
And the third compound is stable.
Yes, the third compound is stable.
That's what we
right. Otherwise, we go back. So you have the
the so-called microscopic reversibility.
Yes.
It's detailed balance.
Exactly. And the barrier height is the enzymes.
Yes.
How do you actually modulate the rate?
How do you want to do that?
Exactly. So you have to inject the enzyme at the right concentration so you can make the reaction.
Yeah.
So it's more like the free energy.
Exactly. So to achieve this, it means that any type of computation has to go from this lower curve, which is at a higher rate, to rate which R equals to 0. So depending on what learning algorithm you choose, it will follow this trajectory or this trajectory. Yes, so this depends on the type of learning algorithm that you're pursuing.
This is even though we just it just occurred to me that we can actually make a device like an industrial device, put it in an SEM and actually control this process and show that you can actually do this learning. Yeah. This is something that I contemplate doing with one of my colleagues. But so this is useful because we can tie it to algorithmic construct.
Yes. The MEMS service is actually chemical
transfer. Of course.
So it is much more amenable to this. And I would argue phase change also.
Also phase change, of course. Yes.
So there are different trade-offs in following different trajectories. So here, for example, this trajectory for computational learning means that you're making, you're doing computation very fast, but you're not memorizing, you're not keeping track of memory. So you have to make sure that you start addressing the retention pretty quickly at the end, because otherwise you will forget what you have learned. Right? Whereas this trajectory takes both the trade-offs into account. It moves the computation forward, but also memorizes what it has learned. Okay, so that's the trade-off between the two, the speed and the barrier trade. The second key result is now connecting this with learning. Okay, so how do we connect this with learning? And we'll make tons of assumptions here. Again, the idea is that initially there's no barrier, and then as the learning converges, you increase the height of the barrier. So you are only modulating the barrier here. We will assume that the learning proceeds using gradient descent. Okay, so we will only use that. So WD is the weights, N is the time index. And this is simply the gradient descent. Epsilon in this case is the learning rate. So first, if I just follow the chain rule, I calculate using calculus. Okay, I'm just applying the net change in the loss function is equal to that. And then if I plug in the expression of the gradient descent into this, what will happen is that this term will become squared. Okay, so it becomes something positive, which is equal to energy. And then I have normalized this with KT over D just to convert this loss function into energy. If the loss function didn't have any units, so I just added the unit associated with it. I could have chosen any other unit.
So what is D?
D is the
number of parameters.
Oh, D is
number of parameters.
So just you can think of it as
dimension of the system, if you can.
No, I mean the length that it takes to diffusion length be
or the
rather velocity effect.
Okay. Yeah, so here I just chose the dimensionality of the problem. So D in this case, the number of parameters in this case. Okay. So once I have parameters has to do with
how does it tie to the trajectory? What parameters?
Yes, so what it's saying is that now to make these electrons move, that energy is coming from the loss function itself.
Right.
The field gradient or the gradient itself.
I know, but when you talk about parameters, you mean the parameters to describe that curve there that you showed?
Yeah, so I'm assuming that the loss function is a function of these parameters. Some arbitrary.
I see. Oh, I see.
Okay. And then why is this important? Because what we are saying is that the gradient information is encoded in the energy that is available in the network to push the memory. Okay, there is no external energy that you're applying there. Okay. So these two are related, and this process is kind of self-sustained. All we are doing is modulating the barrier in this case.
So it is the gradient of the energy. So there is a force,
yes,
the electrons. But if you need a gradient of the energy, you still need to be applying energy as a function of time.
Only initially. So you initialize the network, and then you let the electrons move according to the gradient, the potential field.
Right, but your barrier should be increasing.
Yes. So what we have to do is to be able to control that barrier.
Right.
Exactly. So that's what we are saying is that, and how do we predetermine how we control the barrier? So that's what we are asking.
And the barrier is both the retention time, but also the learning rate.
And the learning rate.
And the noise as a learning reception.
Yeah. So noise at the final retention state. So initially noise is actually good for us. Thermal fluctuation is good for us initially.
And that is because?
It's because it can explore many different trajectories. Okay. So we are not fighting the noise initially. It's the retention part. Once it has learned, that's where you have to fight the noise.
So doesn't that assume?
So there would be learning. Typically,
would apply things like drop out, drop connect. So drop connect would be effectively synaptic noise. And so rather than doing that artificially, you can take advantage of the natural noise present in the system.
So doesn't the noise assume that you are sampling the paths as you are going to the end? But there's also noise in the other way.
Other way meaning?
That is between the source and the.
No, so what, that's why we are saying.
So that means
it's like
the electrons may not be
yes,
exploding.
Yeah, it's like a random walk.
Coming back.
Yes, it's random walk.
Right.
It's random walk. So all we are saying is that whatever
just add some component, otherwise you have to skip the distribution.
Exactly. So even if it takes different random walk, all we want is
the gradient will have to be maintained.
Yes. I think there is
so basically what you did there is a transformation. I mean, I'm just looking.
Yeah.
You went from the delta Ln and you rewrote the Ln as an energy.
Yes.
And then E is E.
Yeah, and then we will plug in this delta E.
If you look at your equation there,
yeah.
KT over D.
Yeah.
I mean, D is diffusion, and that relates basically.
Well, in this case, dimension, or you can talk about degrees of freedom. But yeah, it's not.
D is not diffusion.
I know, but the unit's there.
No, D is a number of parameters.
But I think if you have a microscopic system that is moving and assumes a length Ln where you are updating,
yes,
when you relate that to the energy of the system, and the energy of the system is KT, I don't know what you relate it to, then D now, KT over D.
Looks like diffusion.
It is, which is really actually, if I go back, is a mean length between collisions.
Yes.
Well, you are saying mean feedback.
Mean feedback.
Yeah.
Yeah.
No,
yes.
Yes. So I have used this D in a general way. I mean, you can interpret it in many different ways. Okay, there's another group that is waiting for us.
Fascinating.
Yeah. So if we plug in this delta En into our previous relationship over here, okay, and making the assumption that the gradient is always bounded, which is reasonable for most learning applications, okay, we end up with this relationship which connects the height of the energy barrier to the rate of computation and the learning rate. Why is this important? Because in the first few slides, I showed that there were these bottlenecks, right? The rate at which the computation procedure or the rate at which you have to update the memory is the update wall. Learning rate is what determines the consolidation wall, like how the hierarchy of memory, what you need to keep in memory for a long time. Okay? So it relates, both these parameters are related to the height of the energy barrier. And remember, our goal is that as the learning proceeds asymptotically, the computation rate should go down, and then the learning rate should also go down. That, it's essentially you are consolidating all the parameters that you have learned. So if I plot, and there is many degrees of freedom at which I can make this happen. Rn can go to 0 in many different ways. The learning rate can go to 0 in many different ways. So what I have plotted here are different profiles. If R goes to 0 as epsilon squared, epsilon 1.5 takes these different curves. What I see from this relationship, the height of the energy barrier increases, which makes sense because initially, as the computation proceeds, so you want the energy barrier to be low because you're dissipating less power initially. But then as the learning stops, you are entering into the inference phase, the higher barrier height has to increase because you have to retain the parameters that you have learned. Right? So that's what this is kind of showing.
The other thing is looking at Landauer's formulation versus this one.
Yes.
It's very tempting to think the right hand side has some kind of entropy, right?
Yes. So if I take a special case of this, like when Rn is just scaling of this, what will happen is that using this limit, you will have this epsilon, you can use L'Hopital's rule, this energy barrier becomes equal to something similar to Landauer. Okay, something equal, it's a revised Landauer. This is the energy that you need to dissipate for training, fundamentally.
So then what is C?
C is some constant that I've chosen, that you reduce the rate by some linear parameter of the.
So something of
Yeah.
that's actually learning in memory.
Yes, you're actually learning.
You're not even, it's not about connecting something. Exactly.
Yes, exactly. Yeah, I will stop over here.
I assume some familiarity with that's people who have trained already like neural networks, and I'm going to go more into the details of what the differences to SNNs are. Yeah, I posted the link to this tutorial in the chat if you also want to run it online. So we're going to import a couple of things. So what we want to do is we want to already in simulation have a user neural model that is the one that is on Speck, right? So this is a simple integrated fire neural model. So Steve already gave the introduction to Speck. And we're going to use the Synapse library. So this is our library for vision applications and has the support for Speck hardware. Yeah. It's not very visible, no? Okay, okay. No, that's a good point. I didn't think about this. Theme. I love this. Light. Well done. That's it. Okay, maybe even a bit bigger. Better. Is it visible? Yeah, good. All right. Okay, so just to show, like what the how an integrated fire neuron behaves. So we're just gonna put some random input into a single neuron here, and we're gonna plot that. And if you have some random input spikes in the first line, then on the second line, we're tracking, second plot here, tracking the membrane potential. You can see it has like no leak, a perfect integrator. And whenever it reaches a certain threshold, in this case 5 here, we output the spike. So this is our neural model that we're going to work with. And we're just going to do a simple NNS classification. We use a data set transform library called Tonic that to load our data set. So if you don't have that already on your computer or wherever you're running it on, we will download it for you. In this case, I have it already downloaded, and we're going to use a representation which is essentially histograms. So we're pinning these events to frames. Here we say that we want to have a fixed number of 30 frames per cover. Okay, we want to have 30 time bins, regardless of how long the samples are. But because we know that NN is 3 milliseconds long, that works just fine. And then another thing, this transform here, we're also going to just convert to float, so that when we convert to tensors, that the patterns can work with this. Oh, yeah. Then, if we have a look at the first 10 frames here, no, exactly. This feature is supposed to be here. This is the first saccade, first of the 3 saccades that because NN is the 3 saccade motion of digits of NS, right, on the fringe. Okay. So, okay, then we reassign this trend. And we're going to wrap that into a data loader. Now, when you just work with the data sets in Tonic or Torch Vision for that matter, you can load single samples, but when you want to train larger data sets, you want to benefit from like multiprocessing, like prefetching, so like some acceleration, like you can also like in memory and like, so there's a couple of things that these data loader Python data loaders suppose that help you load data file. So we're gonna also use that. Batch size of 16, nice. And now we're gonna have a look at what are the shapes now that we're working with. So from the train loader, we have a single sample here. We have a batch size of 16. We have 30 time steps. We have two polarities for on-off and X and Y dimensions, or let's say the sensor size dimensions, right? X, Y. This is a 5D tensor. Now, if we work with convolutional neural networks in PyTorch, conv layers only take in a 4-dimensional tensor. So that's a problem. So this thing doesn't fit in there. So there's a few different approaches to get around this problem. For example, one thing that you can do is you just put a for loop and you just loop, you feed single time steps of your model. Single time steps of your data to your model. This is, for example, how SNN torch. Or what we do in Synapse is that we say we just flatten these first two dimensions and essentially treat all the time steps as independent suffix. So because the convolutional operation doesn't depend on the state, the conv2D operation doesn't depend on the state, so we can get away with it. Yes. I think so.
Street is not recognizable.
Are you on Zoom?
Yeah.
No, it's not being recorded. Okay, no, it's recording, but I share your screen.
No. You're on VPN, right?
No.
Why is it trying to connect it?
Well, I don't know. So it says that I'm sharing. I mean, I can stop share.
Oh, I see. Okay.
I can share again.
Okay.
So I think this what you see.
No, I think you're sharing it and it's in recorded. So we're good recording.
It's good now.
What network are you using?
What's that?
What network are you using?
Yeah, so gonna come to that. Just the next thing is that whatever. So
that was not the network question.
Sorry.
Ethernet.
I see. This kind of network, Java.
Should be fine.
Gonna train Gamma. Okay. Yeah.
You said that you basically treat the events as independent, something like that.
So the time steps.
And so how do you work with the fact that in order to integrate they should be?
Yeah, very good question. So it's a very good question. So what that means is, so now the conv2D is a bottleneck. Okay, so the conv2D only fits 40 tensor, but as you said, we need to integrate over time. So there, we need to work with the 5D tensor. So then what we do is we flatten the input just before conv2D layers, and then unflatten it again in these integrate and fire squeeze layers. So basically, the IIF squeeze layer is aware of the batch size. It receives the 4D tensor, unflattens it. So basically, it has a 4D tensor and then makes it a 5D tensor again because it knows the batch size. And then it can process it sequentially. So then this layer has a for loop in there, which goes over all the time steps.
Okay, but it's after the convolution layer.
It's after the convolution layer. Why do we do that? Because in that sense, we can treat the convolution one shot across all the time steps in order to speed up things, right? Yes.
There is that, and the second thing is we don't have to write another tiny convolution layer in our name.
So there's other ways around. You could do 3D convolutions with specific kernel, or you can do a specific, you can write your own sequential, like Morse does it. Okay, so all because complete only takes in for you and function. Yeah. So this is specific to Synapse. So that means now if you work with a convolution layer, whatever squeeze version of your neural model, it could be lift squeeze or adaptive lift squeeze, and it will do the unflattening for you. Okay, so then you can also use just a normal sequential Python sequential. So this is our network, and we can choose a backend for our network. So by default, we are going to use the normal Synapse backend. This is basically this pure PyTorch. It has this for loop in there, and then does its thing under the hood. Now we also have an efficient implementation to speed up gradient computation, led by Felix here, and so I want to also show you the difference in timing to train these things. But let's start with Synapse backend, so pure PyTorch. Here I just feed one of these sample inputs I feed to the model, and to just show you what is the output dimension. So the output dimension now is 16 batch sizes, 16 30 time steps, and 10 output neurons, because we are doing SNNs. Okay, so now we are already at the training step. So fairly, your standard code, you choose your optimizer, choose your criterion, and for however many epochs you would like to feed your data, you move it to the right device, reset the states for here, in this case, between each sample, and feed the data to the model. And then what you get here, Y hat, is what we saw earlier, like the study time steps. What we say here is that we're just gonna average across all these time steps to get our predictions, or whatever the neuron that fires the most is of interest. So now I just want to draw your attention to the speed here roughly. So we have here roughly 14 to 15 iterations per second that it can process on this GPU. And now, if I change the backend with a simple command. So the important thing here is that the API of these two packages is exactly the same. So you can leave everything the same. Rather from Synapse, import this neural model, say from Synapse Exodus, import this model. So now we're going to have an Exodus model, which behaves exactly the same, but uses GPU, like an efficient GPU implementation. And now we went from 15 iterations per second to 7, 8 iterations per second. Exactly the same gradients. So this is the contribution of Exodus on top of Slayer. So Felix identified that there was a certain part of the reset kernel that was neglected during the backward pass. So that when you had very tasks, we were training tasks that needed very long memory, it would the gradient computation would not be accurate, it would not be like EBTT. And so Felix went ahead and fixed that for us. And so now we get the same gradients as your normal EBTT implementation, but just in much. So that's what we use to train ourselves.
This work on how many neural models does it work on?
Yeah, okay. So currently there's diff there is so the integrated fire, leak integrated fire, adaptive leak integrated fire, so this with an adaptive threshold, and we also have just a leak integrator without fire.
I think adaptive integrated
is
not
supported. Yeah, right. So,
So it's supported by
Synapse.
Synapse Madox.
Yeah, yeah, right. Other questions for that? Okay, so this was just a single epoch now, and we're already, pretty low loss here. And I'm gonna now run the testing phase. So this should give us some hopefully decent accuracy. Let's say, okay, 96%. And yeah, this is the basic setup of how we train our models. Now there is some tricks that you can use for to speed up the data loading even further. So sometimes, let's say you want to use some augmentation, or let's say you want to transform your data in certain ways. You want to apply some cropping, or you want to generate time surfaces, or then if you do that for every sample in every epoch, this is wasted computation, because what the transforms that we do is essentially you cache these samples. So you essentially pre-process them once, right? Then you generate these pre-processed samples, and then in the next epoch, you just use these pre-processed samples. So these cache samples, sorry. In order to just like leave out the deterministic transformation stuff.
In terms of time surfaces, the samples are between layers, so
so this here is only for inputs.
Oh, inputs, okay. So you cache them.
The caching is only for the inputs. Okay. So then when you want to work with Exodus, the caveat is that you need to have a GPU on that machine, because it's custom CUDA code and therefore it needs to compile it. So you need to have CUDA on the machine. If you like I do here, I run this on a remote machine, and I want to deploy the model now on my local machine, because this is where my chip sits. So then on my local machine, I don't have CUDA. So then what I do is we have like some conversion API where we can just say we want to convert from Exodus to Synapse. All the parameters are going to be the same. It's just that it doesn't need a GPU backend in order to load it. That's it. We save this. It's done. Any other questions so far? So now what I want to do is deploy our trained models on chip. For that, we have another sub-library, all part of the Synapse ecosystem, called Synapse Dynamic CNN. And this is essentially the connector to our chip. So then when we start off with our trained model. And there you go, we have it. So we have our parameters in here. And now the chip, maybe if you remember what Sadiq explained, the chip has 9 cores. Each one of these cores groups specific layers. So each one of these cores has a convolutional connectivity, a spiking layer, and the pooling operation. So now we already took that into account during training when we set up our network. We set up in this way that sequentially these layers can be nicely grouped together. It's always like these three different kinds of layers. We have conv, spiking, pooling, conv, spiking, pooling in the sequential. And then when we convert it now to a model that's compatible with the Dynamic CNN, with Speck, then it will have a much easier time. So there are some things that you need to take into account. Maybe I should also say that there's some things that we need to take into account during training in order to increase the on-chip performance. Notably, these are if you have like so the more fine-grained your time steps are, the less discrepancy between simulating a model on synchronized, on a von Neumann system, or let's say on a synchronized on a GPU, such as this one, and the chip. So finer grained time steps typically helps. Then we have these like the architecture, so that you take into account like conf spike pooling. Then another thing is about setting a minimum threshold. So, for example, if in your simulation model you don't set a negative threshold, then maybe these neurons just go to super low values, and then on chip this is not really possible because you want to quantize your thresholds, and if you have a very large, if you have to take into account very large negative value, then you reduce the resolution of this threshold. So you want to also during simulation cap the minimum negative value. And another thing is that when you work with spikes, and they are not typically amenable to max pooling or average pooling, because average pooling you need time ideally, and max or also for max pooling. So then what we just use in our simulation already is sum pooling, where you just you sum over a specific spatial area, and then this is also naturally supported on chip. So there's a couple of these things. If you take those into account, it's going to make your on-chip performance much better. Okay, so now we have that, and now we want to convert it to a model that's compatible with to give the input shape, and that's more or less it. And now it's going to do this conversion for you. So now you can see that it grouped your sequential into these 3-layer groups. So the first one here is just to do some downsampling if you have some specific filters for your camera. But in this case, we're just going to go directly onto the random CNN, the backend, the accelerator part, right? To run our workload. We're going to inject the events from the computer rather than the camera. So then you have here this first layer, you have the convolution, the spiking, and the pooling. And for the spiking layer here, you can now see that it automatically discretized the threshold. And because in the simulation, I set the threshold to 1 and -1, these numbers here are now also equal. Okay. If I hadn't set that, then I think so if I don't set the negative threshold, then it will take some example input and test what then the maximum negative value will be, or how will it determine the smallest negative.
So if you do not set the threshold, essentially it is the least number that can be possible.
Okay, nice.
It's 2 power -15.
Nice. Okay. So if you set it, then essentially you increase your dynamic range of the threshold value.
And more importantly, it helps the neurons from not going into this deep hole, which it will take forever to recover from. Because essentially your neurons are sitting somewhere super polarized. Then you need very much positive input to recover. If your data is changing rapidly between classes, you'll never be able to detect anything.
then now let's move this model to our device. So our API is also, you know, like the PyTorch's API, where you say, normally you say to CUDA or to CPU, we just say to Speck to dev or whatever chip you are playing with. It's going to do some validation, so it's going to check, does this model fit into memory? Are these layers okay? And then it's going to move into the chip, and it is now on there. You can also check the memory set summary. So because of the structure of how, like, you know, more high number of neurons, but then in the later layers maybe have higher number of connectivity, then the memory is also not equally distributed. So this, but it will automatically find like a good match for your network. So you don't have to worry about that too much unless your model is very big. And yeah, so then now we're going to take the events, the original events from an MNIST, and then we're going to convert them to Speck events, so to say. So to represent, I mean, it's essentially more or less the same thing. It's just that these Speck events are can be understood by the FPGA. So now I'm testing my test set on chip. You can see that on the, like, down there, bottom right, you can see the test accuracy as a, like, it's updated on the fly as we test more samples. Now, yeah, so as this thing is also shuffled, so then, yeah, so we can see that basically what you can see is that the test accuracy is, you know, as we expected, like even better than our original model in this case. Maybe it will go down once it goes to some of the other digits. Yeah. So yeah, I think that's a short introduction on how to train and deploy the Speck.
Where is the chip?
Yeah.
Where is it running?
Where is it running? So it's beneath there. Do you think we can like give it a run?
You don't have a GPU on that, right? Oh, you train somewhere else.
Yeah, I trained on the remote machine. Exactly. I trained on the machine in Zurich, and then I just downloaded the model, and the deployment, yeah, is easier if it happens locally. Yeah.
So this demo performs optic flow on Speck in real time. It's an interesting demo insofar as optic flow is quite a temporal task. And if you think about our neural model, integrate and fire, non-link integrate and fire, so there's a very reduced or almost next to none temporal dynamics in that neuron model. And so when we started doing this, we weren't actually sure if optic flow would work with that, but it here. So what we see here is actually the input to the DVS. We see Gerd waving, and yeah, you also see the resolution is somewhat low. I think it's pooled down to 64 by 64. And here's the interesting part. So that's the optic flow field that is being predicted by the model. So you will see these arrows. We don't have a full resolution optic flow. We only do 4 by 4. In this case, to make it a bit easier, in theory, you could also probably have higher resolutions. And yeah, as Gregor is showing, it works. There is a tiny, not so tiny lag, which comes just from the plotting of these arrows. So when you move very quickly,
these arrows will be a bit behind, but that's really just the plotting on the laptop. And one cool thing, so that there was the presentation by Guido on optic flow for drones, where they looked into the divergence for landing. And so we also wanted to give that a try with our model to make sure that this also works. And that's actually the case. So for example, when I move now my phone closer to the camera, you will see actually this divergence in the arrows here.
It's kind of deep learning with spiking neuron models. So we can go ahead and, I'll take a step back and explain from a more basic POV. Google Colab is a notebook environment, a great sandbox for playing around and testing bits of code. A lot of tools, a lot of libraries have been pre-installed, so you don't have to necessarily worry about having to set up a virtual environment and installing all the libraries you need. So things just tend to work with that's nice. What's even nicer is that you get free GPU access on it. So that's all well and good. I'll be using GPUs on that. So SNN Torch is hosted on Pi. So we can hit install it. Got some plotting settings as well. You can hit play, and that's gonna just a bunch of code that we don't really need to go over. But with that being said, what am I going to go through? Probably not go through everything here. 40 minutes. Bit of leaky integrated fine neuron stuff. So everything I talked about in my other extended talk, just a little bit more detail. We'll go ahead and train a spiking neural net classifier. And I think this bit is kind of interesting. So loading in your own data and training a spiking neural net with that data. And so that data is coming from Hugo. I'll let him briefly give an overview of what the data structure is. We are assuming that that data is in a NumPy array format. And then depending on how we go with time, a couple of fancy little concepts, probably skip over population codes. A few fancier neuron models. Learning precise spike timing was pretty easy. I think I went over that the other day. And then if you want to do hardware-friendly training, it's where you have lightweight neural nets with fixed precision weights as opposed to full precision weights, then it's actually really easy to swap them out, swap out your layers and be able to train stuff. So the leaky integrated fine neuron, I'm probably not going to spend 20 minutes on this. We'll see. Very fancy. All right, so importing a bunch of libraries here. Now that I've installed SNN Torch, I actually have to import it in order to have access to all the functions and all the spiking neuron models in there, right? So every time I call SNN, I'm going to have direct access to all the stuff in SNN Torch. Spike plot, splat is going to let me plot some stuff in PyTorch as well. So I press Shift Enter to run this code block. Now, what I want to do, I did this earlier, but in like 3 seconds. So we'll spend a little bit more time on this. So if I want to construct a leaky integrated fine neuron, if I'm going too fast for anyone, just stop me. This is assuming that we're kind of starting from very low level understanding. If I want to instantiate a leaky integrated fine neuron, that's really easy. So if there's a leaky integrated fine neuron within the within SNN Torch, and we just call it leak. But we have to insert a few arguments because we can parameterize this leaky integrated fine neuron. Now you recall that the leaky integrated fine neuron has some sort of state, right? I want to inject that neuron with some input that changes something within the neuron. And if that something is sufficiently high, then that neuron is going to emit an output spike and stuff gets transferred to downstream layers. Now, before we consider inputs and outputs, there's something inside that neuron. There's the membrane potential. The membrane potential is going to evolve over time. Right? You excite your membrane potential, and then you remove some stimulus, and then we expect some exponential decay. You expect some funky dynamics. What do those dynamics look like? Now, we kind of abstract from all the physical plausibility away to just this one variable called data. If I say I want a decay rate of 0.8, what does that mean? If we discretize time, setting my beta value to 0.8 implies that from one time step to another time step, The first time step will have, or the second time step will have 80% of the membrane potential voltage as the previous time step. So if I want a really fast decay rate, I would crank that down, right? Like my voltage was 1, and if I had a decay of 0.1, then it would jump down to 0.1 volts at the next time step, right? So 0.8 means that you get a little bit of lingering membrane potential as a result. Question?
Yeah, but this is only one neuron or it's a neuron population?
This is not specified yet. So the way that this works is, I'll get to it. Yeah. So we instantiate this leaky integrated fire neuron or neurons. We haven't actually specified whether we have a single neuron or a population of neurons. That ends up being dependent on what you pass in to this layer. That doesn't make sense, that's okay. We'll see this in action. So my leaky integrating fire neuron is contained within this variable called LIF, right? Leaky integrating fire. Now let's simulate one single leaky integrating fire neuron. How do I do that? So I want to simulate it over some number of time steps. I'm going to set it to 200, so 200 discrete time steps. Then I'm going to apply some input current stimulus to my neuron. So let's break this down a little bit. So torch.zeros is just going to give me 10 zeros. Torch.ones is going to give me, well, got 190 here. So I'm going to get 190 ones. And that's all going to be scaled by 0.21. It's just a nice number, as you'll see. Actually, you know what? I'm going to take it down to 0.18. And then I use torch.cat to concatenate the zeros and the ones together, right? So we have current injection to start with nothing, and then it should jump up to 0.18. It's kind of dimensionless, to be honest. So we also need to initialize our membrane potential and our spiking output variable. This is where we start to factor in how many neurons are contained within LIF. So in this instance, I might just say torch.zeros. I want one neuron to start with. So I just have one membrane potential because there's only one neuron, right? So I'll start at 0. Spike, there's no reason why I should start with a spike, so I'll have 0. Zeros once again. And I'll run this.
Where did this guy discuss the important stuff, right?
Now, next, what I want to do is generate a pair of empty lists. And the goal here is, as I simulate over time, I'm going to be generating a trace of membrane potentials and a trace of spike variables over time. And I'm just going to store them and populate the list. It's going to get longer and longer as we move forward in time. So that's cool. These are empty for now. We haven't recorded anything. Next, I want to actually simulate this again and again. So I apply the current injection at the first time step, which is 0. Remember, we had a bunch of zeros. I apply that to my leaky integrated fire neuron, and then I get a new membrane potential at my next time step. I get a spike variable at my next time step, and I just do that again and again, and we get some recurrence, and that's how we simulate over 200 steps. So what I say is the step in range num steps, remember num steps is 200, then I need to do something, right? So the step in range num steps. So I have my leaky integrating fire neuron. We've created it. It's got the decay rate of 0.8. Now we're actually going to call it. We're going to apply some current stimulus to it. That's X. We're applying X. But recall, X is a tensor. We want to apply one input at a time. It doesn't really make sense to already have access to all of our inputs and to pass every single input over time in one step, right? We want to chunk out every time step of our current injection. So to do that, we just index into step. Right? So step is going to iterate from 0 to 200, which is 199. So we're going to keep incrementing through that tensor of X. Is that it though? There's one more variable that we need to pass. That's the membrane potential. So we're going to keep on updating the membrane potential and then letting the neuron know, oh, by the way, this is your new membrane potential. So this LIF neuron, this leaky integrating fire neuron, is going to give us 2 variables in return. It's going to give us spiking variable. It's going to give us the new membrane potential. So just to clarify, X is a one-dimensional tensor, a few zeros, and then a current injection is applied to a number of elements of 200. We pass that in. And we also pass in a membrane potential. If that membrane potential exceeds a threshold, then we get a spike for 1. And we also take membrane, scale it by 0.8, scale it by beta, and we get a new membrane potential. And then we just do that again for every single loop. Now we also want to record a list, right? So we have membrane, we want to append membrane into it, so we're just populating the list, right? Do the same thing with spike, right?
Is the threshold default here?
Say that once again.
Is the threshold default value here?
Yes, great question. So we've got a bunch of defaults, right? In this case, your default threshold value is just set to 1. You can change that, right? If I was to go back into LIF, actually, you know what? When we construct a network, I'll show you an example of how we change that kind of thing. So by default, your threshold is just set to 1. But if I go ahead and torch.stack converts this list, eventually we'll have a list populated with values. It just converts a list into a tensor. We want a tensor because that's what PyTorch is compatible with. Then we plot everything that we have. We plot our input current stimulus, we plot the membrane over time, we plot the spike and everything. So hit shift enter, we run that for loop. And what do we see? We see a current injection. This makes sense. We had a bunch of zeros, which jumped up to 0.18. Then we have a membrane potential that exponentially relaxes to some value. It just missed the threshold, right? Just missed the threshold. So it makes sense that we see no spikes. So let's go back and redo this. Get out of my face. So let's crank that back up to 0.21. So we're just going to nudge the current injection a little bit. We're just going to redo that simulation. Perfect. So we get a current injection a little bit higher this time. Now, in this instance, we see the membrane potential reach the threshold, and then we have a reset mechanism. So model biology is it good for deep learning? Don't really know, to be honest, but promotes a bit of sparsity. And so you end up seeing this rate-based firing mechanism from that one leaking integrated by neuron. Now, if I was to, so X was previously just one value. X step was just one value. So X was a list, and when I index into a single value of that list, it just ends up being one value that I pass into LIF. Membrane was just one value as well. Remember, we had torch.zeros, just one dimension. If I was to say, create torch.zeros with 20 values, and I decided to create this X current injection to be 20 values by 200 values, so 200 is over time, 20 values, that would imply that I have 20 neurons and 20 neurons. If the 20 neurons, I need 20 membrane potentials to be instantiated. So this function infers how many neurons on the basis of what you're passing to them. Okay. Any questions so far? Yeah.
Is there a refractory period as well in the IF?
No, no, there is no refractory period hard-coded into it. This is simplest therefore is type of LIF neuron. You would be able to kind of wrap a class around your leaky integrated fire neuron and force the input to be nulled every time there is a spike. So you have a spike and you say, okay, if there's a spike, then for 3 time steps, I want to force my input to be 0, therefore my output. So you can kind of need to hard code that if you want to do this.
For instance, of the neuron itself is stateless, right?
Say that again.
So it's just a function of this state neuron itself.
Yeah, so the state in what I've shown you here, the state is external, and you pass that in. If you want that state to be abstracted away and to be a class variable, the instance variable, then there is a trick that you would play that I've accounted for in, where is it? In this here. So I would go initialize hidden. So that means your hidden state is going to be initialized as a state variable. I would go true, and then I would no longer need to pass my membrane in because that's in the back, being processed in the background. I prefer to not do that just because I like having access to everything. If I want to do residual connections, if I want to do more exotic architectures. But in my view, it's better practice to just have access to everything. But some people just want to quickly code something and not have to deal with it. So if I'm doing an NN.sequential constructor, if you don't understand this, don't worry about it. If I have an NN.sequential constructor, that assumes that one layer passes one variable to the next layer. One variable to the next layer, and in that instance, you have to set init hidden as true. Because you can only pass spikes between layers. The membrane potential needs to just run in the background. Good question. Okay, so that's how to create a single leaky integrated fine neuron. That was 10-ish minutes actually, not 5. So train an SNN classifier. I'm going to call a bunch of libraries and modules within Torch, and then the map and several neural networks. So we have a lot of neural network layers there. Data loader lets us have access to a lot of data sets from within PyTorch. So it lets us use data sets within PyTorch. We can transform data sets into shapes, sizes that we like. So we run that. Now this is a bit of boilerplate. We'll just show you how to train an MNIST data set before we go on to brain data. Now, loading the MNIST data set, how many of you have like 0 to very little deep learning experience? So if I asked everyone what's a batch size, you would be able to tell me. Nice. Anyone ashamed of not knowing what a batch size is? Okay. You're good? Okay. So we parallelize our data sets, pass 128 chunks of data in at once to speed things up because we have GPUs, they like parallels. So here, let's just say we have 128 samples being MNIST being passed into our network at once. We save it in some folder, which is going to show up here, I guess. Well, this is kind of boilerplate. This said, if we have access to GPUs, let's use them. Otherwise, let's just use CPUs. If you're on a MacBook M1 or M2, then use, I think the stands for like metal performance shader or something. So that's the line of code you would use if you're running locally on a MacBook and you have whatever GPU.
Sorry, there's an unrelated question. So for this map one, is it accelerated or?
Yeah. MPS is just the Apple GPU, silicon, whatever. I'm not too sure. Yeah, do that if you're running on a MacBook GPU and M1 or M2. Then we apply some transforms to the MNIST data set. So for context, MNIST is the data set. It's considered a toy data set. We don't really benchmark it in fancy papers anymore because it's considered thoroughly solved. But it's good for debugging and just showing things work. Each sample of MNIST is a 28 by 28 image, grayscale. And then so, yeah, what are we doing? Just ensuring it's 28 by 28, ensuring that it's grayscale, but casting it into a tensor because PyTorch likes tensors, and we're normalizing every single pixel value between 0 and 1. And what we're going to end up with is a data set stored within MNIST underscore train and a test set stored within MNIST underscore test. Then the data loader is going to chunk these up into batches of 128. So we have a data loader, a train loader, and a test loader, I guess, and test loader. So that's all well and good. Now let's construct a fully connected spiking neural net. I asked this question the other day, how many inputs do we need? If MNIST is a 28 by 28 image, how many inputs do we need in our network? Yep, 28 by 28, 784. Hidden neurons, we can just go 1,000 arbitrarily. Number of outputs, 10 digits, 10 outputs. Temporal dynamics, we want to keep this quick, 25. Beta. Empirically, I know that something large works very well. There's no temporal information contained within MNIST. It's just a static image. So this doesn't really matter. As long as it's not 0, so that it's kind of canceling out the membrane position, it doesn't really matter. So let's just go 0.9. Doesn't really matter. Now let's define our network. This is where boilerplate starts to kind of ramp up a bit. We're going to put it into a class called net. We're going to inherit a bunch of functions from nn.module. We're going to have technically 2 spiking layers, but consider each spiking layer to be attached to a dense layer of weights. So fully connected one is just going to be a linear layer where we have our 784 inputs connected, where every single node is connected to our 1,000 outputs, right? So that instantiates 784,000 weights, right? Then we're going to take all of those outputs. We're going to take those once we finally pass in our MNIST images into this layer, we're going to come out with 1,000 current injections. And those 1,000 current injections get passed into our leaky integrated fire neuron. So we've got to instantiate our leaky integrated fire neuron, just like before. Let's just say beta equals beta. Now, that's right. If we want to change our threshold, threshold is by default set to 1. You can do whatever you want. Now, in practice, if I find that my network isn't training very well, I'll try dropping my threshold a little bit or a lot in order to ensure that the current injection does promote and elicit spikes. Because sometimes the reason my network isn't trained is because spikes just don't get propagated through. The current injection is insufficient to meet the threshold, therefore my network is kind of dead and there's no output spikes. So I could set that to 1, I could set that to whatever. Another couple of functions you might be interested in, if we want beta to be learnable, then we just set learn beta equals true. If we want the threshold to be learnable, we set learn threshold to be true. A few other functions, I don't think we really need to look into them. You can change your reset mechanism, the subtract, reset to 0, no reset, which we would say none. And then there's also the idea of a surrogate gradient, right? I mentioned that in order to have gradients propagating backwards, so in order to perform gradient error back propagation, we have another argument where you can pass in particular surrogate gradients. There is actually already a default surrogate gradient embedded within these neurons. That's the arctangent function, just because it works well. But if you want to try other surrogate gradients, then you would do something like import from SNN torch, import surrogate, and then I would say, let's just call it surrogate grad equals surrogate dot pass sigmoid. If I want a pass sigmoid function, we choose the lowercase one, and then I would just pass that variable into Speck grad. So you can specify what kind of surrogate gradient you want. I will not do that because we already have one in the background set by default. So then we generate a bunch of spikes. Yeah.
So what is the role of a surrogate gradient?
It's to overcome the non-differentiability problem, because recall that we have a hard threshold, right? When you apply membrane potential to when you apply an input current injection to your neuron, you get dynamics with your membrane. If that membrane potential exceeds your threshold of 1, then you trigger a spike. If you think about it mathematically, that looks like a heaviside step. So if your voltage is above the jump of your step, it's a shifted heaviside step. If it's greater than the step, then you generate a spike, you generate a 1. If it's below the step, you generate a 0. If I take the derivative of that heaviside function, then it's just the Dirac delta. Everything is almost everything is 0. When you apply the chain rule in order to do back propagation, it's basically like taking that 0 and multiplying every single gradient signal by 0. What happens then? If I have 0, if all my gradients are 0, then I can't update any weights with those gradients. Well, you can, it will just not make any change.
So just replace it for training, and then you are back to previous model for inference.
Exactly. So during inference, everything is always using the heaviside step, but during the backward pass, that's when you replace the heaviside step with the surrogate function. Yeah. So then I have a bunch of current injections from my next layer, and we just kind of repeat this. So we go from num hidden to num. Was it output or outputs? Outputs. So that's going to have 1,000 times 10. That's 10,000 weights, and then SNN dot leaky beta equals beta. Then we have so that's what our neuron looks like. So that's what our network looks like. But we need to specify how data propagates through that network every time we call it. We've instantiated a bunch of layers, but nothing tells this model how they're structured. So I need to do that myself. So first thing we have to do is initialize our hidden states. Now, because so within every leaky integrate and fire neuron, there is a class method that lets you arbitrarily instantiate the membrane potential and all of your initial hidden variables. So I don't need to know the size of my input data in order for this to work. But this is a good kind of trick that I use all the time. So self, what is it? So within self.lif1. So I'm just going into my leaky integrating fire neuron, and there's a method within there, and it's hidden. So I haven't specified how large its membrane potential is going to be. It's going to figure out the moment I pass data into it. So it's kind of like I've instantiated a tensor, the membrane, but it's kind of dimensionless. And once I pass data into that neuron, then it decides what the dimensions are going to be. Then I just do the same thing with mem2. Then I
starts with a random number, or
just nothing. It's just nothing in there. Yeah.
It probably is a stupid question, but when you define your network, you are using some layer from the normal PyTorch, right? That is
Yes.
the spiking, right?
Yeah,
And
exactly.
you combine with the
SNN layers, yeah. So the idea is that you generate a current injection. That current injection is then passed to your spiking neuron. So the current injection is like taking an input pixel, you weight it, that generates current, and that current is passed to your spiking neuron. So in a way, it's kind of like if you combine FC1 and LIF1, then you have a leaky integrated pi with learnable current dynamics in a way. Very good question. Okay. Now, we've instantiated stuff. We've got a list because we want to get our output spikes. We want to get our membrane spikes at the output. Now we have to do a time loop because we're passing data that's 25 time steps. So what do we do first? So recall we've got FC1 and LIF1, and we have FC2 and LIF2. This is a fair bit of, I'm just going to kind of fly through this, right? So we're passing X as our input data. And we're going to just pass the same X value at every time step, because remember, MNIST is not time varying. If it was time varying, then I would iterate with discrete time, but it's not time varying, so I just pass an X into FC1. That needs to be self.FC1. Then out I get, well, let's say the current injection, right? Can anyone spot any mistake here? Quick, go for the question.
I just went to the documentation, and it says hidden as an argument which you give to the one.
Sorry?
It is hidden as an argument which you give to the neuron one.
Oh, so that's an option. So it is an optional argument.
But how do you call the argument for it?
Oh, right. So init hidden is an argument. Let me try to remember what's init leaky. My man, thank you. You know my library better than I do. And thank you. I relinquish all IP rights of SNN push to the two of you. Yeah, so yeah, we call init leaky. Thank you. So init hidden is the argument that we use to instantiate membrane in the background. Init leaky is to generate the shapeless tensor that will then be defined once we apply an input to our spiking neuron. So we generate current from an input X. Anyone spot any mistake? If I was to simulate this, I'd get an error. Why?
Two-dimensional rate.
Exactly. MNIST is a image, 28 by 28. I need to flatten that 28 by 28 into a 784 dimensional vector. All right. So that's pretty easy. I go flatten. In PyTorch, the dimensions of your data go batch size. Remember, we had 128 samples being passed at once. Batch size times the dimensions of your data. So we've got our batch size, which is our 0th dimension, by 28 by 28. But by flatten, I don't want to flatten from 0 because I don't want to merge the batch size with everything else. I want to keep my batches separate. So I want to flatten from the first dimension. So the first and second dimensions get combined. So the 28 by 28 gets combined into a vector. So we go from batch times X times Y into batch times every pixel, right? So then our current is going to be, we're going to have 784 current values, and then 128 samples, each of which have 784 currents. So we'll end up with a 2D tensor of 128 by 784. I'll write that here. So we end up with batch size of 128 times 784 current values. Then we're going to pass this into our spiking neuron. So we'll pass the current injection, but we also have to pass in the membrane potential, so mem1. And that's going to generate two output variables. We'll call that spike1 and mem1. So mem1 is just going to keep getting replaced and being updated over time. Then we can do the same thing with fully connected layer. We're going to pass the spiking from the previous layer into our next dense layer. That generates another current, and that current is going to be used hopefully I don't run into any errors. So then I've got Speck 2, mem 2. And finally, I want to keep track of all my values. So I have the recordings that I'm going to make. So I've created 2 empty lists. And so I'm just going to append every new value of my spikes to that list. And we'll do the same thing with membrane potential. Then this final line is going to just return the whole list converted into a tensor. So by the end, what these should be are tensors that are 128 batches times 10 output neurons. Actually, no, yeah, so 10 output neurons. But because we're simulating this over n time steps, we're going to be appending 25 different values of spikes. So we end up with time by batch size by number of output classes. And the same thing goes with the membrane potential, that we're going to be of the same dimension. So then I've created my network and I'm just going to store it in lowercase net. Let's run that. It takes a moment. So the first time that you call your GPU, it takes a second to run. So here I haven't really done the, yeah, so for everything from here onwards is just cheat stuff. So we call the loss function cross entropy loss. I won't go through the math, but the idea is that if I have an image, I'll use an example. Let's say my input image is the number 3. Then I consider my output layer. I don't want my 0 neuron to be active too much. I don't want my first neuron, second neuron. I want my third neuron corresponding to the number 3 to be the most active. In non-spiking neural networks, then it means you have some full precision value coming out of that third neuron, and we just want that to be maximized. So it's kind of like the cross entropy loss. What it does is it takes the exponent of the full precision number coming out of that third neuron. So it exponentiates it really large. Then it divides it by the exponent of every single output summed together. So that kind of normalizes. So if you were to take the summation of all of those exponents, then it would kind of be normalized to 1. So in a way, it can be represented as a probability. And then the idea is that you pass it to a log-like language function that's just trying to maximize the full precision value from your third neuron. So explaining like in 5, you want your third number to have the largest output number. Right? You want your third neuron to have the largest output number. In the spiking world, what's coming out of that neuron? Spikes. So you could go a few ways. You could say, hey, I want my third neuron to have the most spikes. So if I had like 20 spikes, but with 25 time steps, then this cross entropy loss will try and make that 20 spikes into 25 spikes. We'll just try to maximize the number of spikes coming out of my third neuron, and it will try to squash the number of spikes from every other neuron. So it maximizes your predicted class and minimizes everything else. And so in that way, you kind of have a rate code, and that's all well and good. And an alternative strategy is to apply this to your membrane potential, where if I was to maximize my membrane, then that should also equivalently lead to the most spikes, right? Yeah, the neuron with a very high membrane potential, it should always be above the threshold in a way, and therefore you get more spiking out of that particular neuron. At the same time, for your incorrect neurons, it's going to try to suppress the membrane potential down to 0, therefore no spiking. So then we interpret the neuron, our predicted class, to be the neuron with the highest firing rate. So if I have a neuron with 25 spikes, and then another neuron with 20 spikes, another neuron with 3 spikes, I will assume that the network predicts my input image to be the neuron index with the highest spike count. We're looking at the neuron with 25, or just the most number of spikes relative to everything else. Does that kind of make sense? So then we have an optimizer, add an optimizer. I won't go into too much detail, but this just defines how your weights are being updated. So once you have a gradient, do some stuff to it, momentum, parameters, and then you just update your weights, scale it by a particular learning rate. Don't worry too much about that. Just for the sake of doing something quick, we're going to do 1 epoch of training. Now in the MNIST data set, there's a total, in the training set, there's a total of 60,000 samples. We're doing this in batches, batch sizes of 128. So if I divide it to it's 468 point something. So this training loop is going to go through for every epoch 468 times. I'm going to terminate it just a little bit early, just for the sake of getting through this. Now in practice, you would have an epoch loop. You just want to keep training this for a while. So within this epoch loop, we're only doing this once, so technically I could delete this. We don't need that outer loop. I take my train loader. Remember, we put out all our data, our MNIST samples into little bite-sized pieces of 128 samples. So I'm creating an iterator out of that, putting that in train batch. Now, train batch just has like this, it's not a list, it's like a PyTorch alternative constructor where every element of this, whatever curious little data structure, has a data and it has a target. So each data sample has a label associated with it, and that label is the ground truth. So if I have an image of 3, then I'll have a number that says 3. And my network is trying to take that 3 and say, cool, make it a 3rd neuron spike. If you see a pattern that looks like the number 3. We load them up onto GPUs. We set net to train and say, yeah, track your gradients. And then all we do is pass our data into our network. That network is going to return 2 variables. Remember, we had our spike recordings over time. And it's also going to return membrane potential. In this case, I'm going to ignore the membrane potential. All I need is my spikes. Then I need to calculate a loss out of that. So we're going to have 1 loss out value. So I instantiate torch.zeros. We start off with 0 loss. And then what I do is, I do want this because other reasons. So then what I'm doing is summing up all the spikes over time. Remember, so I'm going to go spike recording, sum it in the 0th dimension. Now remember, my 0th dimension is time. Right? So if I collapse that time dimension, then I'm left with just batches times my number of output neurons. So then the maximum number I can have is 25. If I have a neuron spiking 25 times, the maximum number I'll get is 25. And so I have a loss value, 25. And then you compare that against your ground truth. Your ground truth will say, I want my 3rd neuron to be the maximum, to have the maximum spike. And these 3 steps basically take that into consideration. These compare your spike counts versus your label. And so that's kind of all abstracted away. Optimizer.step will go ahead and update your gradients. And here I'm just going to break out of that loop after 100 iterations. So if I go ahead and run that, yesterday, a couple of days ago, this didn't work. Let's see what I get. Cool. So we're seeing the loss go down. So within a matter of a few seconds, we're seeing something that actually trains. That's all well and good. This has only been trained for 90 or 100 iterations. Now I've put together another function to measure the accuracy on the test set. Yeah, on the test set. So what this is doing is just taking the model, passing the data into it, getting a spike recording, getting a spike count out of that recording if you sum in the 0th dimension. And then we pluck out the max of the index of the neuron that has the maximum firing rate. So that's all this is doing. We're just querying our outputs and saying which neuron fired the most. And then we're saying, did that match the label? If so, you got it right. If not, you got it wrong. So every time we get it right, we kind of add an extra reward and say, yeah, cool, well done, you did well. So we go ahead and measure the percentage of correct values. And so we end up with 92.4% in the matter of a few seconds. So, and this is very easy. Put in a little bit more effort, I can train something a little fancy. Now, I'm not going to go into too much detail, but if you want to get better, if you want to do better, then we use convolutional SNNs. And the approach to training that is the exact same as the linear classifier. You instantiate 2D convolutions. One is your, what does all this mean? 1 is your channel size, 8 is your output channel size, 5 is your kernel size. If this doesn't make sense, that's okay. We can chat about convolutional sizes later. That generates this 3-dimensional current injection. That current injection gets passed into your leaky layer. We max pool it to downsample all of the data, our features. We just do that a bunch of times. Don't worry too much about the details. I won't bother running this because it takes a little bit longer, but that's still fine. Any questions so far? Awesome. So I'm just gonna, yeah, this is where the fun begins. We don't have too much time, right? So now we're going to go ahead and play with brain data. So I might get Hugo to come up and just quickly explain what this data looks like.
I need to be in the audio group in 4 minutes, so it's going to be a really fast one. Do you have like the data on the number, because I couldn't get it to load.
Oh, okay.
Yeah, exactly.
Oh, yeah.
It just generates like around like right.
No, I can go ahead and upload it from.
Yeah, in the meantime, I'll explain. So I guess like there's 2 sides. There's the biological side that I guess we don't really care about, and there's this practical structure for the sake of this tutorial. The idea that the data is here, basically, you can think of it, it's like EEG, but intracranial. So what I did is that, like, I performed surgery on the, let's call it just the brain for the moment. I performed surgery on the brain, remove the skull, and then so you have access to the brain matter, insert an electrode into that. And there's an electrode, so that's going to be measuring the field potential from the neuron. That's like the ionic movements whenever there's a spike. I threshold that to be more efficient. I threshold that, and then you just get the spike counts for a bunch of neurons in response to a particular input for which you have the ground truth. And so basically, based on that, you can, have your basic decoding, like, and this type of data sets. You can think of it as like 12 different digits shown to an animal, and the spike in response at a bunch of time in response to that. I guess that covers it, yeah?
Yeah.
So basically, the structure of the file, yes, good stuff.
So emulate that.
And the structure, like, the way it is, right? It's like time steps in one dimensions. So like the evolution of the firing rate of 250 neurons, I guess, and they're labeled, yeah, that's right. And so like they're in batches of 32.
So say that again. So we have 61 time steps.
You have 61 time steps, like that's the evolution of the firing rate as a function of time, like post stimulation time, right?
Yeah.
249 different neurons that are being simultaneously recorded in response to one stimuli.
Yeah.
And 32 be the labels of those stimulations.
The batch size.
The batch size, that's
Yeah.
the batch size.
Yeah. 32 batches, 61 time steps, 249 neurons.
Batch is the experiment here.
Yeah. Right.
So I'm sorry, is 249 neurons or like 249 neurons?
249 neurons, just like less electrons than neurons. It's just like long chunks you can record multiple neurons at the same time, right?
Okay.
No, that makes sense. Cool. Awesome.
I'd love to be
Great timing. Cool. So if we wanted to train a network to go ahead and try and interpret what number is being seen based on EEG data. Now, I haven't put together an accuracy function here, but so with all of this here, if you have EEG data or any data set that isn't natively within PyTorch, you can reuse a lot of this code on this drive in order to make your stuff happen.
So networks work. You gave the tutorial and you told me you're not gonna do it.
I'll give you a one-on-one. The Slack was like going back and forth. I was like, cool, internet works, shit, internet doesn't. Oh, it worked. No, it doesn't. Fine. Yeah, so here we are.
Okay, yeah, I fix the network just for this situation.
All right, guys, so we're gonna start again for Andreas to say. No. So we have this custom data set. I actually got ChatGPT to write this for me. I said, hey man, I have brain data in this shape. This is what my dimensions are. Can you please give me a data loader that is compatible with PyTorch? And it gave me this, and it worked out in 2 iterations. So we now have 32 batches, 61 time steps, 249 neurons. Let's go ahead and train a network. How do we define this? As 249 inputs, right? 249 readings from that many neurons. Same architecture, but this time we have 12 digits. And same as before, 0.95. I don't need to go through this. We're just going to use the same spiking neural net. The architecture is the exact same. The only difference is this time I'm going to loop over a different value, right? And that value is going to be in the first dimension of my input. So let's refresh our memories. This is the 0th dimension. This is our first dimension. Therefore, that is our number of time steps. We're going to iterate 61 times during that forward pass. We're then going to step through the first dimension as well. Right? So we've got a colon indicating keep your batch intact, only iterate through that first dimension. Nearly done. Then we end up with a recording of spikes and membrane potential. And we load that onto CUDA. It's all well and good. We're just going to use the same cross entropy loss function as before. And I'll go ahead and train this. Now I haven't optimized this. We literally put this together minutes before the tutorial, but you can see that something is being learned, right? We're seeing some loss metric go down, but now it's gone back up. Clearly, this is somewhat unstable. It's a far more challenging task than next. But if I wanted to go ahead and measure accuracy, we have an alternative function to do that for you. Now I'll skip over population codes. Within that same notebook, I have a tutorial on how to train using neuromorphic event-based data sets with Tonic. I think this example is the POCA DBS data set, which is super easy. an alternative neuron type, your recurrent leaky integrating fine neurons, where output spikes are projected back to your inputs through different mechanisms. One thing that I do want to show you though, can I have 5 more minutes? So one thing that I do want to show you here is if I go back to my MNIST fully connected SNN example, and I want to train a fixed precision network with weights that are no longer full precision, that are no longer floating point, which is what PyTorch likes. The way that I would do that, so thankfully Xilinx have already created a library for this. It's called Brevitas. It's pretty well documented. So you can install Brevitas and then, what do I do? So from Brevitas import, I think it's going to go to my cheat sheet. I don't remember this. So go to, perfect. Import brevitas.nn as QNN. Your Q naturally stands for quantized neural network. Now I need to find that again.
I mean, but these are fixed, they're not spiking, I mean, they're just regular.
This is just weights. Right. Actually, a QNN is only extension. And full disclosure, these are not fixed, they're not actually fixed precision weights. They are full precision weights that have been quantized into various levels. So it's like having full precision, it's a fixed precision representation using full precision variables, right? Because PyTorch ultimately is not compatible with fixed precision natively. You have to do a few other things to make that work. But the idea is that if you at least find the most appropriate levels, your min and max of your quantized state, then it works easily. I almost got it. So we import our quantized layers, and so it's just a matter of going QNN dot quantized linear, and what is this variable? Num bit width. Kind of used to Colab just telling me what's going to come. No. Let's scroll back down. So the variable name is weight bit width. So if I want 8-bit weights, then I add that in. Then if I want, and we've got to do that with everything else. QNN dot quant linear. So I'll go ahead and run this, right? So that requires one. All right, so it just wants to know explicitly if I don't want to include a bias. It doesn't really matter for this simulation. Bias equals false. So if I go ahead and run this, now that works. Hopefully this works as well. Perfect. So we've got something running. So what's going on? Every time I pass this batch of data into my quantized construct, then it's going through all of the weights that are currently present in full precision. It takes the minimum weight, it takes the maximum weight, and then uniformly distributes 256 levels, true to the power of 8 levels between them, and then it uses that during the forward pass. And during the backward pass, it updates your full precision weights, and then it just repeats that again and again. Now, that's all well and good. That's for your weights. Of course, with SNNs, you've also got additional variables that, and I mean, our spikes are 1 and 0, right? That's fine. You can introduce graded spikes and have quantized activation. That's fine. Your stage,
Brevitas doesn't do a uniform quantization.
Yeah, by default, it's uniform quantization. They don't have exponentially distributed quantization. But yeah. An alternative variable that you might want to be quantizing is your neuron state, right? I've found a lot of quantized SNN papers that kind of ignore the state here. So I've done a few tests, integrated quantization aware training with your state as well. I'll go ahead and scroll down and not rewrite this. But the idea is, okay, so within SNN, so PyTorch has this module within it called functional. Likewise with SNN Torch, you have a module called functional. Quant has a bunch of dirty little functions that help you quantize things that are not available in conventional neural nets. So all I do, it takes one line of code and one additional argument to quantize your state and to do state full aware quantization. So quant, I have to specify how many bits I want my state to be constrained to. Here, I have included uniform and non-uniform quantization. The motivation was Right? Do I want more states clustered around my threshold? Do I want more precision at the point of spiking? Or do I want that around zero? Because you have a reset, and so most of our neurons spend a lot of their time at zero. What matters more? In practice, we've actually found that non-uniform clustering around the threshold is way, way better. And if you set your minimum, rather than setting your minimum value to the minimum current projection, you just set it to zero because your negative threshold, we don't have negative thresholds here. So that seems to work. That's been very good. We now store that information of how we want to quantize our neurons in QLIF. And then I just pass QLIF into each of my spiking neuron constructors. And I can do because I don't want to do anything different between the two leaky integrating fire neuron layers, I just pass the same thing between the two. And then bam, I've got quantized states as the result. So that's all well and good. In practice, when I'm training on DBS gesture, fashion MNIST, I see that with quantization where training of weights, I get a 10% boost over first quantization training. With stateful quantization aware training, I find 1 to 2% boost. So weights matter a hell of a lot more. I arguably wasted a shit ton of time running that experiment to see how well it performed. But that's the spirit. I think that's more or less everything that I've got here. Any questions? Yeah.
The difference of the quantization and the SNN states is running noise, or does it behave really differently?
Say that again?
Okay, well, thanks for waiting. I hope this will be worth the wait. So I wanted to show basically some highlight reels of what we're doing with event-based vision in, let's say, the real world. I mean, the real world is a bit of a, we're all in the real world, but, you know, try and do some applications with it. And part of that, I think it's so important, is there is more interest in neuromorphic engineering and more funding in neuromorphic engineering now than there has ever been. I've been in this field for over 30 years. And it's amazing how much interest there is in it now, and how much funding is available to do projects and to do research. But if we don't deliver on some of those promises that we make some applications and show we can do some stuff in the real world, it's going to be considered hype, and it's going to go the way neural networks went in the early 90s. And so let's try and avoid that. And so I'm advocating to let's try and do some real things, not just Formula One robot cars, but real cars or real applications, right? And I'm not saying we shouldn't do the other thing, right? I'm saying we should also try, even if there are simpler problems. So here too, a lot of it's still vision.
Afford to do. That's why we do F110. It's a serious competition against other teams that are seriously. So if you can prove that you can win at that, you're.
Yeah, that's true. That's true. Yeah.
It's not, it's not an arbitrary.
No, it's not a line following. It's not a line following robot like we have had in Telluride for decades, right?
Which was fine, also, right? At that time, it was fine.
Yeah.
Because other times you had a camera that wasn't actually doing anything.
Yeah, but if we're still doing the same projects, right, then we haven't made progress.
No, we're not. We're not doing the same project.
No. That's why it's in, right? So anyway. So let's hope this now works. Yeah. So several of you will be aware that we're using event-based cameras for tracking satellites in space stuff, and that came out of this footage that you saw here. I'll try and go back. We were putting it on the back of a telescope. And we were playing with biases and looking at it, and something shot through the frame of view. This was done in Adelaide during the day, actually. We went, hey, what's that? And that was the first satellite we saw. Some of you, if you were in Telluride in 2017 or so, I think, we borrowed a telescope from somebody local here and put some stuff on the telescope and did some experiments with that. So we've been working to further that application. When we started this, I wasn't aware that with satellites, you need to look at them to keep their orbits predictable. I thought it's in space, like the planets. Once you know their orbit, you can predict them 1,000 years ahead. You know where they're going to be. But with satellites, it's based on that's not true at all. They're subject to solar winds. Of course, their mass is a lot smaller than that of a planet, so they're much easier to move about. And some of them can maneuver, actually satellites do maneuver, that's how they stay up, because particularly low Earth orbit satellites, if they don't push, they'll just slowly descend and will burn up. So, and when you do this optically, you're looking through it with a high power telescope, you're looking at this tiny bit of the sky, like we're looking through a straw. And so if you know where to look, you can find the satellite. But if your prediction is wrong of where you should be looking, good luck finding that thing, trying to search for it. So it's important that pretty much everything that's up there gets eyes on at least twice a day. And there's a lot up there, as you know by now, and more being put up there at a faster and faster rate. So with the event-based camera here, we're tracking it, which is actually not the ideal thing to do, obviously, because if you keep something perfectly still in the field of view with an event-based camera, you're not going to see it. What you see shooting through are the stars, so they'll all shoot through in the same direction if we keep tracking this rocket body in the same direction.
Sorry, what's on the right side?
So on the right side, it's an XYT display. So you got the X and Y, and time is a vertical axis, and color is also time, just to make it a bit more colorful.
Oh,
So the color and the time axis are redundant in that sense, but and you can see we're not perfectly tracking it. Obviously, with stars and satellites too, if you keep them perfectly still in the field of view of an event-based camera, you still get events from them, because you know, if you look at the stars, they twinkle, they flicker. That scintillation that you get, that's because of the atmosphere and turbulence in the atmosphere. So you still get some light changes, but not as much as when they move through the thing. So with event-based tracking, we actually want things to move, not too fast, ideally, but there needs to be some motion, so you generate nice events. So this is where we started back then. For comparison, this is how it's traditionally done with standard cameras, frame-based cameras. You take like an exposure time of a second. That's why you see all the stars are streaks. And you take a shot every 5 seconds and you're tracking this thing. Can you see where the object is? That's that. No, that's the star. It's moving just like the other stars, right? And now it jumped all the way up to here, right? So you also have a correspondence problem, right? You don't know exactly what belongs to what.
You mean the small circle that's central, that's stationary?
Yeah, that's what we're tracking. And it's not so visible until you start doing this.
Yeah, that's a
wow. Yeah, and that's a trick we've learned for displaying that I'm using later as well. The human eye, human brain is very good at moving things, whereas if you do this slow, 1 frame every 5 seconds, it becomes fairly meaningless to us. It's because it's not a continuous motion anymore. So we use that. Yes.
So when you move, we saw some bright spots not.
Yeah, so they're the ones that are the things that are being tracked because they have kept stationary in the image.
So they are like satellites or like.
So they're satellites or a rocket body or whatever. Yeah. I mean, they could also be hot pixels on the camera, right? So if you have fixed pattern noise on the camera, it's also not going to move. Yeah. So that's another reason why keeping things perfectly still in the field of view is not necessarily the best thing to do. Okay, so we developed this into a solution where it's in a, we converted the shipping container, and it has a sliding roof, which is basically a garage door, somewhat modified. And then there's a lifting platform in it that will lift the telescope out on a robotic mount, and it will point at the various places in the sky, as you'll see in a moment. The nice thing about shipping containers is there's a whole industry that moves shipping containers about. And so we can deploy these things, ship them anywhere, put them up. Within one night, we can have them operational. You need a night because you want to calibrate with known stars, but where you're looking. This was in the desert. You see the wetness that I was mocking up there. Whenever you put an optical telescope, even in the desert, we bring rain. So it's also a good rainmaker. This seems to always happen. So we set it up here. It's sort of calibrating itself against known stars in the sky. And so it's nice. It's also, defense is interested in it, or intelligence. they want to know where satellites are, and they also want to know where adversary satellites are, obviously. And if you do this with known astronomical observatories that are there, they're usually on top of a mountain, big concrete slab, big building, everything made sure so that the telescope can be very stable and very still.
Are you tracking a single satellite or multiple satellites?
Depends.
What's the interest?
Depends. Mainly single satellites to get to update their orbit for catalog maintenance. So, that's probably the main routine task. And then it's new things for, like if something new goes up, for creating an initial orbit. It's rare to track because you have such a small field of view. Like if you look at the geostationary satellites, the ones that give you your TV and your network satellites. So they're far away in this geostationary belt along the equator, about 36,000 kilometers away. And they're often, if you're looking further away, you have a larger field of view. You see multiple satellites in the same field of view. The local ones like Starlink or the International Space Station or something, they're only about 400 kilometers above the Earth. So you see a very small part of the,
quite fast
actually. And you have to be able to track pretty fast with that as well. So it's, as I was saying, so it's nice to not have to be able to just work from these astronomical observatories, because there an adversary could know that, oh, I'm not in the field of view of any of these observatories at the moment. This is where I'm going to move my satellite, and then they're all going to lose me. With these, any ship and container that could be standing around the world could be an observatory. So good luck predicting where you're not visible, right? So we automated it. So this is where there's a schedule. I mean, it's sped up, but it's a schedule where it's doing these observations. And I hope it's a bit light here, but I hope you can see the objects that they're doing that are the stars, and the objects that are shooting up are the satellites that we pick. I mean, this is massively sped up. And then at the end, you'll see when it's done, it packs itself up again, the container. And this is an indication of, this is only a subset of the satellites that are visible from this point of view at any point in time. So it's so busy up there that it's incredible. I mean, there's a lot of space in space. So then we've developed algorithms to say, okay, these are the stars, automatically label them. This is an object that we're interested in. And then we can find the position of that object relative to the stars with microsecond precision. Well, microsecond resolution, I should say. The precision is less than the microsecond, obviously. It's not as quantified.
It looks like comets, right?
Yeah.
Like they're trading.
So when you see here, we have both the stars are moving and the satellite is moving, but in a different direction than the star. And that's one of the reasons we do this. And so the star field is very well known. So then if you know where your object is, the stars are making a nice stable basis. Earth doesn't make a good stable basis because we're rotating, we're spinning. So it gives us good accuracy of telling where these satellites are. So we have 2 of those. We're just started building a 3rd one. So if you have 3, we can start doing triangulation as well. So then you can start looking at distance of satellites. And we're in the process of commercializing this. So in the next few months, I hope we have a company up and running that will start doing this and deliver data as a service, basically, to do satellite observations that commercial and defense clients might want us to do, and catalog maintains and just upload that data to some central database. There is a world central database for these observations and also the predicted orbits. So that's one commercial application. So then,
just a quick question there. That observations, are you doing that mostly during the day, during at night?
Mostly at night, because it's a lot simpler at night.
Okay, but
we want to start doing some during the day, but I don't know how well it will work. We have some examples of where we see during the day, but obviously you're going to have less contrast, right? So the contrast at night is very high, which is nice for us.
Since we are speaking to the practical relevance of the problems, I want to know, the event-based cameras are good at doing this, but are they better than what the non-event-based alternatives would be? Is it due to the dynamic range, or did you try it with like, I don't know, like expensive high frame rate cameras or stuff like this?
Well, you can do high frame rate cameras, because then you need very short exposure times. And if you do standard cameras with very short exposure times, you see nothing. So you can do it with smaller ones, but then you don't get the temporal resolution. They work as well, and they often have a bit larger field of view. Like if this application goes big, we would want an event-based camera with large pixels in a large area, so that we can have a larger field of view and maximize the number of the amount of light each pixel connects. So you'd optimize an event-based sensor for it. At the moment, we use the Prophecy Gen 4 because it's got the best resolution for it, and also the best sensitivity because it's got the best fill factor of all the event-based cameras out there. Okay, so this some of the stuff that we showed with the satellite tracking. So particularly Greg Cohen, who's going to appear here and tell you magically any moment now. Only for tonight, so one night only performance. We started showing this around. This got interest from the US Air Force, and then we started the collaboration with the US Air Force Academy, which is here in Colorado Springs, and with NASA, which allowed us to take it to the International Space Station. But before I go there, you see on the right, how do you get to the space station with a rocket? So we thought, well, let's look at some rockets with event-based cameras. So here's some footage. Event-based camera on the left, a decent Sony standard camera on the right. This was real time, the playback. This is slowed down by factor 20. And you can see the regular camera, the exposure, the auto exposure is just still not good and washed out.
Is the color spectroscopic?
The color is blue is on, yellow, yellow is on, blue is off, changes in the event camera.
Oh, okay.
And then there's a bit of a decay time constant on it because it makes nicer images. So
can it do chemistry?
Can it do chemistry? No, not at the moment, but we are looking at different filters in front of it and so on, and then you can start doing it. So with Toby, we've also worked on the polarized version of event-based cameras, for instance, working the polarized light. I'll play this one more time. Again, it's not as good on Zoom as that's a bit fast. Sorry, that's so it's not as good on Zoom as I'd hoped, but still, you can see fair amount of detail here. Here too, we get a few artifacts when the rocket ignites, but here we can see the launch and the exhaust, and you see a few things puffing out, and then up here the stabilizer rockets, which give the rocket a spin, kick in somewhere here, there, and it starts spinning the rocket, and like that camera recovers when the rocket is out of view. Another advantage is, so when you do this at our launch site, you can't just set up your camera 5 minutes before the rocket launch. They don't want you anywhere near their stuff, right? So we set this up hour and a half before or so and let it run, and you can speed up how fast you want to play this back, right? And then if something interesting is in this thing, like a, like a shooting star for luck, that just comes there, you can slow down and picture that. So and then you can speed it up again, so that if you want to look at the footage where something interesting happening, you display that faster. And with the launch, so now you can see that this is event rate. There's total event rate on the camera. And you can see when there's bumps happening, that's some clouds shooting through. The stars are moving because we're just staring up and the Earth is rotating. We're doing about 5 minutes per second here in the footage. That's why and you can see something big is coming here in the event rate. So that's the rocket launch. So it's very easy too, if you want to find an event that generates a lot of events, then you can easily find it in your data just by looking at the event rate and know where you need to look.
Your axis is kind of deceptive because it's logarithmic, right? I thought initially it was linear.
Yeah, no, this is logarithmic, yeah, the data.
Yeah.
So we're fairly underneath with this setup. So in a moment we also get totally washed over by the exhaust and the smoke from the thing. So it disappears a bit. Like here's a good wash. coming up, and then you see the second stage igniting on that rocket, and it's shooting off. So this is at the moment not commercial. It was just we had the opportunity. NASA was launching for the first time in a long time, I think, some rockets from the northern part of Australia, from Nullarbor, Ireland, and so we went up there and just shot some footage. So then we are on the International Space Station. We have 2 cameras there. We took the cameras we knew best for that. Typically, if you go to space, you don't take the newest gadget, but the one you've worked with the longest. So that's a Davis 240 by 180, but we're only using the events out of the Davis. And one camera is looking down, and as it looks down and it moves, you can start generating an image of where the changes are happening. And in the scan direction, it has quite good resolution still, because you just like the old photocopier, right? You just scan along and you figure out what the image is. You can get decent resolution. In the cross direction, your resolution is whatever your pixel resolution is. If you're not winning in that direction, you can't do sub-pixel resolution, which is why, in retrospect, we should have mounted this that way, so then at least we would have had 240 pixels resolution and scanning. But anyway, so this is from a camera that's mounted near. So it's here on the International Space Station on the Cauwenberghs module. I don't know exactly where this camera is, so it doesn't have exactly the same field of view, but close. And then we overlaid that on a Google Earth map. This was done during the day. So this is South America. Here the coastline. And you can see the features and also some of the clouds that are generating on events and off events, and the coastline in here. So we can do that with event-based cameras from space making. Yeah?
So when you see events, is it some kind of a specific wavelength, or are they looking at the entire resolution?
It's visible light and near infrared and it's but it's very near infrared. So it's standard CMOS sensitivity curve. And you're just looking for changes in contrast. And if it gets brighter by a certain amount, you send an on event, and if it gets darker by a certain amount, you send an off event.
And the time duration, is it like a continuous?
Yeah, it's in continuous time, but then it gets time stamped on the camera at microsecond resolution. That's in continuous time, microsecond resolution, time stamped, but then there is some latency in the pixel response itself, and that latency itself will depend on how much light the pixel is receiving. It gets faster the more photon current you have. This is done at night. So this is the Suez Canal over Egypt. So Cairo is this pigeon here, which we're just missing, and we're building up this picture as we're scanning along. So this is a water body here. Again, I'm just because it's a bit bright in here too. So this is without the background. And this is at night, so it's largely picking up lights. So you can see the lights along the coastline here. And then here, and then the Suez Canal runs here, and you can see some lights through that as well.
How are you getting purple color? Are you going to the smaller wavelengths?
The color is artificial, just us generating the color.
The on and off events again, 2 different colors.
Right.
Yeah, we're just doing the on and off events in 2 different colors.
Showed the lights on, and I thought these are natural colors.
Yeah, no, they match quite nicely, but they are totally artificial. So this is looking down. We have another camera that looks forward at the horizon, and this is raw footage. So unprocessed, and you look at this, and you go like, yeah, maybe something's happening here. See that coming down? But other than that, not a lot of interesting stuff in here, right? It just looks mainly like noise when you look at this.
Are there so many options?
It's a Davis 240C. It has hot pixels up to wazoo. It just does. That's just how that camera was. So the cameras have improved a lot since. This is a model. So, but now
this is at the ISS, right? So the camera should actually be pretty cold, or how is it housed? So
yeah, so
it could be less of an image.
it should be less, but look at it. Look at the big pattern noise on this thing, right? Like the other thing the Davis 240 has, because of biasing, every other row is more sensitive than the other row, you know. So you get this black striping across as well. So this is putting basically a time surface on. So you put every event sets the thing to 1, and then you have a slow decay, and you jiggle it back and forth like I did with the footage of the star, so we can see. Now you go like, holy crap! There's a lot of stuff in here actually. So these are features on the ground. I don't know what this really bright thing is here, but these are ground, and we're moving towards the horizon there. Stuff going up is stars. And then at the top, you see that bright thing shooting through. Well, there has to be a satellite.
And then I was wondering, do you know the effect of radiation? Right, because even though it's outside, it's super cold. I guess you have to run up and that.
So Riyadh did a paper on that, looking at some stuff here, but for the ISS, we have done no radiation hardening or anything. So the thing we did was we took the Davis 240 cameras, kept the sensor and bias board, but took the FPGA board off because it needs a different FPGA to interface with the ISS network, the International Space Station's network, and so on, and certain specs. And that needed to be a particular FPGA, if I'm not mistaken. But that's about it. It's,
yeah, so it could be something.
It's mounted underneath, because it's looking down, underneath the International Space Station. So most of the time it's shielded from solar radiation.
Right, thanks.
So then you can track, so those are stars. So again, we can localize stuff against the stars with this camera already. And then satellites. And the longer you look, the more you see.
Yes.
And there's actually one that we forgot to label. It's going here. See that?
When you say label, what's the algorithm you're using?
Here, for the video, they were done manually, but it's just a self-baked algorithm to track objects through space-time.
So it's kind of better version where you see it, and you're looking for a mask in the image. Or
it's not a learned algorithm. It's an engineered algorithm that we use. So there's no learning in our algorithm that we use for it. And it's just looking for objects that are on a constant trajectory through X, Y, T. And just say those events are part of the same object.
Okay. It's actually optical flow in a sense.
Yeah, I mean.
Now with prophecy, it will be all better, right?
Oh yeah, so I'll get there. So the scientific reason we sent this up, because the PI at the Air Force Academy here, Jeff McGrath, he's mainly studying sprites. And sprites are upside down lightning, basically. It's lightning that goes from the clouds to the upper atmosphere rather than between clouds or down. They can be pretty large effects. And they're a bit hard to study from the ground because you're usually below the clouds. You can't see them very well. He has done some at least 10,000 frames a second. Now, he might have taken 100,000 frames a second camera, but he needs to like charter some planes, some aircrafts to, which if you're at the Air Force Academy might be easier than for general people. But still, it's a real operation to try and record these things. So we were going, can we see them from the International Space Station? I can't guarantee that these are sprites, but there's definitely lightning. So this is city lights. Again, I'm moving it back and forth. So I've reduced the time constants for the decay because the lightning is so fast. So if you look closely, you can see still the stars moving in there. I couldn't detect any satellites in this picture. With the camera that was looking at the ground, as I said, you can build up quite a high resolution image of the ground because you have some time where you scan over the ground. So you can use time to build up that image. With lightning itself is so fast, we can't scan very far while the lightning happens. So you don't get very good resolution with this camera on lightning. So the plan is indeed to look at a better resolution camera like the current one. So this is lightning with Prophecy Gen 4 camera in normal time. So it sees the rain falling. You might think it's odd that the rain goes from white to blue, but here it's the rain against a dark sky reflecting light from the environment, so it's brighter than the background. And here the rain is darker than the background. So it's quick, I'll play it again. Yeah, there's not a lot of time to look at lightning. But if you slow this down, matrix light, where now the raindrops are just coming down in slow motion. It's pretty, huh? So we're doing a fair bit of that now, lightning studies with this stuff, and often you can also see the back propagation, because often where a lightning strike is being charges go back up.
So what did you do to get the second one?
This is just slow down, just same events as in the first figure, just play it back at 400 times slower than real time. So you make the frames, instead of making...
How much time did it take to go?
Yes, it's on here, so it's 8 seconds.
And this distances?
What ratio? Why the angle of the field of view, you mean?
No, what distance?
Yeah, that.
Yeah.
I don't really know, a couple of kilometers maybe.
Do you have a phantom view thing?
No, it's a bit expensive.
For 5 seconds.
Yeah, so and it's heavy, much heavier. You can do it with 100,000 frames a second camera, 10,000 frames a second, but it can record for 5 seconds flat, and then its memory is full. So you'd have to trigger it with something basically.
Yeah, you already ended it, and so the problem is the memory. So do you have an estimate how much data you were generating here with the prophecy at that time frame? Because it's a lot less obviously than for the phantom, right?
Yeah, I mean they're I think a gigabyte max or so, you know, it's not a lot.
But in 8 seconds.
Yeah, I mean a lot of events, right? But still,
the time is 8 seconds.
But if you're waiting for lightning, you're not generating many events. So in that period of time, you're not adding much to the data. It's only every lightning strike that you get lots of events generated. Because for the rest, you just get a bit from the rain.
Show it again.
Yeah, I can show it again.
Yeah.
So you see a bit of artifact from the initial overexposure. You generate a bit too many events for the bus, but then so it first gets bright because of the lightning, and then when the light dies out, it gets black, blue there, right?
Oh, so the blue is when it is dissipating.
Yeah, so it gets bright and then it stops being bright. So when it stops being bright, you get these blue events from it.
At some point, there was some checkerboard pattern that appeared. Is that
that's at the beginning? Yeah, that's when you generate so many events that the bus, like you generate too many events that the bus can handle, and then it starts doing some funny things. Now, if you want to get bored by looking at lightning, you can do a microsecond per frame, because we have the data in microseconds. So each frame that you see here is playing at 30 frames a second or whatever this thing is playing at. And it's a microsecond per frame. And now it just barely moves, right? You can see it growing a little bit, the tendrils and so on. So you can really slow down lightning and study it. So this is what we want to get on the ISS instead, to look at lightning. And we are doing that. So we've got funding to work again with the US Air Force Academy. So we're now building. So this is the first package that went on with 2 cameras, one looking here and one looking in the other direction. The new one will be bigger. It'll have 2 Prophecy Gen 4 cameras in it, and it'll have steerable mirrors, so we can change where we're looking a bit, and a zoomable lens. This thing in the cross direction, because I said in the cross direction, you just got whatever resolution your pixel gives. You can't use time to improve your resolution. It's about 250 meters on the ground. The resolution here, we should be able to go down to 6 meter resolution on the ground. Doing the mirrors was the biggest thing here, because when you start moving things on a satellite like including something as big as the International Space Station. You move it, the International Space Station will move in the opposite direction. And they don't like that very much. I mean, only a little bit, but so you have to counterbalance every movement and so on, so that you're careful that you don't disturb things. And those are things we specifically work with the Air Force Academy with, because they got the expertise of doing this sort of stuff. So that should go up next year. We need to have the design ready, built by the end of this year, and then they do what they call a shake and bake, where they, do mechanical testing and temperature testing and radiation testing, I guess. And again, that will be done here in the US. So that's gives you an idea with Alex just out of field of view, but about the actual size of the thing that will go up significantly bigger than the previous one that was sending. So that's going up next year. The one that's up there was the Davis 240. It went up December the year before last, and it's been giving us since January last year continuous data. We don't always get the link, which we don't get all the data off.
Why is Davis another prophecy?
Back then, because
you're doing a new design, right?
Yeah, the new design is prophecy, Gen 4.
Oh, okay. But it was the
No, the old design is the Davis. No, the new design is prophecy Gen 4 simply because it's the highest resolution one we have at the moment. Maybe at the third iteration when we do this, we get Samsung to pay for us to put it up or whatever with their version of the camera. Might be our Sony, because they're both building event-based cameras now. Then we're looking at the resolution and steerable view. So we had the opportunity actually here in Colorado to fly this with help from a company that makes gimbals for military observations as well and zoomable optics. So this is flying on a Cessna, quite high. And you can see how incredibly stable this, there's nothing to do with what we do, but this gimbal is. But you can track the traffic quite nice. And again, we put a decay on it, so you get these tails, so the cars clearly are darker than the backgrounds.
So how is it that the Cessna is not moving, or is it that?
It is moving. The gimbal is stabilizing the image. That's the Cessna's moving. That's how good the gimbal is. Yeah, it's incredible stuff. And like if you don't put the decay on it, I'm sure we can read like the advertising on the side of the trucks.
The license plates?
Yeah.
Not the license plates.
Well, no, not quite yet. Maybe though. You'll see some later. So this is a guessing game. Those that were at CPPR are not allowed to guess without seeing it. What do you think you're looking at here?
A bridge.
It looks like
Cyber building.
Anybody from Denver here? Okay, you might guess it then. It's in Denver. There's also only one in Colorado Springs.
Yeah.
No, the airport.
No?
Oh, it's a stadium.
You'll see it in a moment, and I'll take it back because then the second time is a bit more interesting to look at it.
Yeah, it's a stadium.
Oh.
Oh, no.
So this is where they're just moving the point of view, right? Can you read this?
Oh,
golf. Top golf. It's a driving. It's a three-level driving range.
Yeah.
So
oh, that's
the horse.
that's a driving range. Oh, yeah, just for practice. I'll take it back a bit. So now you see some of the golf balls shooting out when the people are hitting. Some people hit. Yeah. You see the colors, you see the people don't really.
Yeah, there's no way.
First time I saw this too, it's like, what the hell is this? So it wasn't until the end that.
Is a drone flying?
Yeah, that's the same. It's a Cessna.
But what are
It's not a drone. But it's yeah.
Those are the horns.
Yeah, those are the target holes, right? So
and those holes.
and there's a net around the driving range because there are highways nearby, and so they don't want the balls shooting on there. Right?
There's a top golf in Denver.
No, So you can, and we could do tracking of golf balls, for instance, from a Cessna, which is kind of interesting.
How far away is this? How high up is this?
I wasn't there, so I can't say, but it wasn't this. I mean, it's high up. I'll show you at the end one where I think it indicates how high it is, because there's a recording that starts quite zoomed out and then zooms in. This wasn't at CVPR, but this is just what we did in Boulder with Nick last week. So they have a fluid dynamics lab and they do laser sheet imaging. So they have a powerful laser, some optics that creates a sheet, like a very flat sheet. You can see it hitting the wall behind here. And it shines through water like a container with fluid in it and a magnetic stirrer on the bottom. And they've been doing this with fast frame-based cameras, and we thought, can we look at something with event-based cameras? How well does that work? So we injected reflective particles that reflect the laser light. And you can track the fluid motion quite well if you do that. Again, white is where it gets brighter, yellow is where it gets brighter, blue is where it gets darker, and again we put a little decay on it, so that it's with a standard exponential decay, so you see it decay slowly. So you can get a total flow field from this, right? In this sheet, right? It's not 3D, it's just the 2D part.
Can you go up like that?
We've been working on that, but we haven't got the footage of that, because then you basically do tomography, right? And it's certainly possible, but I don't know at what speed.
Without necessarily going into the medium, right?
This is in the medium. This is at one level in the medium. It's not the surface.
Oh, you put the camera in the.
No, the camera is above the fluid looking down, but the laser is shining, slicing one slice through the fluid. So if you go back here to the so if you see here, the fluid is up to, I don't know, somewhere here, and the laser shines, like you see the edge of the fluid here, maybe? Yeah. This is the edge of the glass, and the laser is shining through the fluid at that level there, just a horizontal slice. And that's the one that you're getting the reflections on when you're imaging.
So it does seem like you could have the laser knows out of that. You can actually.
Yeah, so if you change it down, it's just a question, how quickly can you do that?
That's right.
Right? Or do you use multiple lasers, or different spectra, and you use multiple event-based cameras with different filters? Or
could you alter the focal length of the camera, perhaps?
I mean, the camera is focused to that distance, on the laser plane. Yeah.
What if you could just move the focal length?
Yeah, but you wouldn't see anything because those particles are not being lit up by the laser.
But if you laser lit it up, and then you could, I guess, okay.
Yeah. And the depth of view on these things is not that narrow. Okay. So
you could try something stereoscopic, right? Light up a large slice with a laser and have two cameras.
Yeah, I mean, there are all kinds of options here. So you also see that this is one layer through the fluid in the next video that I'm going to show, which is not these reflective particles, but a fluorescent dye. So the laser makes it fluoresce. It's being injected from the top of the basin, and we're just looking at the sheet. So you'll see when you see the injection, you see some of the fluorescent dye gets injected into the plane of the laser straight away, but some of it will dive under, just because it's inertia, hit the corners and edges of the basin, and then pop back up with the laser sheet. So that's why you see other stuff appearing later. So this is here. So that's the dye being injected, and remember, some of it's going underneath the plane of the laser. And so then it hits the corner and it wells up from underneath back into the field of view.
Yes.
Yeah. Yeah, it's like lava lamp or something like that. Stuff, right?
Like a research.
Yeah.
Like psychedelic.
And you see these typical regions that they talk about in fluid dynamics. Like here in the center, it's really stable. It just keeps rotating around. And basically the whole column rotates. There's no mixing at that level. Then you get a region around it where you get some more stochastic behavior and mixing, and then you get this turbulent stuff at the edge. It was a really good example that if you want to mix fluids, You don't want to keep doing the same movements the whole time because you just build up a stable column. If you want to stir your sugar into your cup of coffee, don't just keep going around, basically. You have to do different movements to mix it well.
Be careful with the spill.
Yes. Don't go too quick. So this is the last one that I have. This is the height that we start at. And just again from the Cessna, and see if you can guess what we're looking at here.
UFO.
That is in the US, that's correct. All UFOs are in the US. The only place it's here.
It's a drone. It's a drone.
It's Superman. So this is specular reflection of water, and that's a boat, and you can see weight. Because we're flying above the water, and at some point you're just getting the sun bouncing right back at you.
So why did it drop like that? So this is
that's just the zoom on the thing that they have. It's just them zooming in because they have this app. I'm sure they don't use our camera to control the app, but they go, I want to track this thing, I want to stabilize it, I want this here in the image, and they can move that so that they adjust it a bit.
It's a little misleading because the camera is also moving and the zoom is moving, so we don't know that's the object moving on this.
Yeah, exactly. So in this case, you don't know whether it's the object moving or not. So again, you see some sunlight on the thing, and then you zoom in. So it's a little bug on the water. You can see it a bit clearer if you zoom in a bit more. And you're like, wow, that's pretty good zoom from the distance that they started at, right? The stop that you saw. And then they bring it to the center and then they zoom a bit more. So you can't really see it here, but on my screen too, you can see ripples on the water and so on.
Yeah,
and
it looks like
and I mean, if I didn't put the time decay on too, I'm sure you can read the name on the side of the boat.
In what case one would monitor
In what case? I don't know, but it's cool, isn't it? that you can do this. I mean, I don't know if there's like, I really don't know here, like it's harder to see, but you get these real wake and ripples and reflections of the water. I don't know if there's information in there that you want to use.
So I guess the argument for the event cameras here is that, I mean, the zoom is through the optics, but you can get away with zooming so much because you're more light sensitive, or what's the
I think you're less, you can tolerate a bit more movement. So even if they can't keep it as stable, which they are very stable here. So you could probably zoom even more because they don't zoom that far with their optics, because then the images get blurry on a standard frame-based camera. But with this, you know, as long as you have some, like you can do some kind of contrast maximization on the imaging of the events, and even deal with moving on. But these gimbal ones, these ones from the air, I've only put them in as a highlight reel rather than as an application. I don't really know that there is obvious advantage for that, because we haven't really played with that. But this is also how we started with the satellite stuff. We just did a recording, tried, can you do it? Yeah, and then you check, hey, and then you demo it to people that are interested in that particular area, and they go, oh, this could solve this problem that we have. Why don't you look at that? And then you go like, yeah, we'll look at that. Give us $1 million. We'll go look at that for you. And then if it's a big enough problem, they will give you $1 million and you can go look at it.